Welcome to APEC. It is March 16th, and I'm your moderator.
One of the two, but
No. There we go. Welcome to APEC. It is March 16th, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on this call, along with everyone watching us on YouTube. So today, Mike McCullough is going to discuss tests of a quantum horizon drive. Nathan Enan is going to discuss classical coupling of gravitation and electromagnetism. Curtis Horn is going to talk about electromagnetic aspects of quaternion theory, and Mike Gamble is going to give us an amazing overview of his graviflyer replication. We're also going to be hearing updates from our lab partners and finishing off the event with an open discussion by conference attendees. So a couple of quick updates before we begin. Today's event is on StreamYard, so if you are watching this, it will be on YouTube. We're broadcasting to the Propulsion YouTube channel, and I believe the Alien Scientist channel as well. If you haven't subscribed, please do so now. You can visit us at altpropulsion.com, and you can view replays, details, and speaker info on the website there. And you can also use the links to subscribe to the channel or however you get to it. You can ask questions using the live chat feature on the right-hand side of the page. We will do our best to ask them to presenters as they come in. One of the things that we found is we have a really healthy chat discussion that goes on during the conference. So I'm not always able to catch things, but we do our best. So without any further ado, I want to introduce our first presenter. Dr. Mike McCullough is going to discuss tests of a quantum horizon drive. He has been working on a theory of quantized inertia. This is very big, and actually there are a lot of people that are really, really excited about this. It explains inertial mass, eliminates the need for dark matter in galaxies, and there are so many other applications as well as propellantless propulsion apps. So I'm going to bring Mike in without any further ado, and we will get things geared up for him. Okay, so Mike, welcome, sir.
Thank you very much. Thank you for inviting me. I still have a bit of a cough, so I have some ginger tea to
yeah, well, thank you. Thank you so much. It has been, so you did a presentation for us, I think like 2 years ago, something like that, but it's wonderful to have you back.
Yes, that's right.
I mean, again, quantized inertia is like, this is one of those hot ideas that people are really excited about. So I'm genuinely really thankful, that you're presenting on this. So you should have back and forward buttons on the slides that you can use. And what I'm going to do is remove myself. I will still be here in the background if you have any troubles, but I will get out of your way, and and I would say take it away, and thank you again.
Thanks. Okay, yes, so hello. So I'm going to be talking about tests of the quantum horizon drive. I'll first describe the theory of quantized inertia. I'll go into a bit of astrophysical proof for it, and then I'll talk about the applications, including, of course, the thruster. So just to go over my background a little bit, I got my BSc in 1991, PhD in 1995. I was a scientist at the UK Met Office, ocean wave modeling for about 10 years. And I've been more recently a lecturer in geomatics at Plymouth in the UK. And over the past 18 years, I've been publishing 26 or so papers proposing this theory of quantized inertia, and 3 books, which I've shown here. So there's a textbook about it, Physics from the Edge, and then I've written 2 science fiction novels based on the theory as well. They're a bit more accessible. Okay, so there is a this is an animation, but it's not actually working, but it's supposed to show that inertia is just a phenomenon in nature that everybody knows about, that things keep going in a straight line unless you push on them. And this has never really been understood, just assumed. Inertial mass is not due to the Higgs field, which only explains the mass of the quarks, a very tiny amount, component of the mass. So I proposed a new model for inertia, which combines relativity and quantum mechanics, but I have to go a little bit into those subjects in order to explain it. So the first thing I need to explain is the quantum background. So Werner Heisenberg, who's shown here, proposed his famous uncertainty principle that states that if you take the momentum uncertainty, multiply it by the position uncertainty, the result has to be more than a very small number, a constant. Actually, Planck's constant over 2 pi. What this means is that if you shrink the amount of space you're considering further and further down, then the position uncertainty decreases and the momentum uncertainty has to increase. So on the very smallest scale, the cosmos has a lot of energy in it, which is sometimes called quantum foam. So virtual particles are appearing all over the place, usually in pairs to conserve momentum. So these blue arrows show one pair. This could be a positron moving up. This could be an electron going this way. And these particles are also associated with quantum waves as well. So I've tried to show that with the red curve here. So there is a quantum foam in the background, like a very intense sea that we can't actually see. So the proof of this is the Casimir effect. Henry Casimir, back in 1948, shown here, he said that if this zero-point field exists, then if you put two conducting plates side by side, very close together, then some of these quantum waves will fit between the plates, like this one, and some of the waves won't. For example, this one, which does not have a node on the plate. This means that the electrons in the plate will move to damp the field, and so this wave will disappear. So this one will also disappear, which means that there'll be more particles or waves, if you like, outside the plates pushing them inwards than there will be inside pushing outwards. Okay. So he said this would be a proof of the zero-point field if the plates move together. And in fact, it's now known, it was first tested in 1997, and they do move together to the degree within 5% anyway, expected or predicted by Casimir. Okay. So in order to try and explain this, I'm going to go back to an ocean analogy. So imagine you have a ship which is parked next to a dock. Now, there'll probably be quite a few waves out to sea over here, but there will likely be far fewer waves between the ship and the dock. For example, there's a wave here which has a wavelength equal to twice the distance between the ship and the dock. And this wave can exist because it has a node at the ship and the dock, so there's no friction, so it doesn't get damped. But the point is to say that fewer waves could exist between the ship and the dock, so the waves out to sea will tend to push the ship towards the dock. And this is a well-known phenomenon in oceanography, the maritime Casimir effect. And it does actually happen like this. So if you're on the ship and you saw the ship moving mysteriously towards the dock, you would think it's some kind of strange phenomenon, but actually it's just the waves that you can't see. So another kind of way to look at this, instead of having a conducting plate, or a dock, you can have something a bit more abstract that's called a horizon. So try to explain this here. This aircraft here is supposed to be accelerating to the right, and there's an explosion behind it. Now, if this craft accelerates fast enough away from the explosion, then the sound from the explosion will not be able to catch up with it. So we could say that the explosion is behind a horizon for the plane. And I've tried to show this horizon here. The position is quite arbitrary, but it can be calculated mathematically from the acceleration of the plane. So the explosion is behind a horizon for the plane. So horizons also exist for light, and one famous horizon is the black hole event horizon. So if you have a lot of matter inside a very small volume, even light isn't able to escape from this particular volume. So we have what they call a black hole. And Stephen Hawking, back in 1975 or so, speculated what would happen if some of these virtual particles appeared right on the boundary, right on the horizon, the event horizon of the black hole. So, excuse me, one particle would go outside the black hole, and one would probably go inside. And the one that goes inside would disappear from the point of view of anybody outside. So the outside particle would now have no twin with which to recombine. So this would be released as what's now called Hawking radiation. Similarly, just a year or so later, these three guys, so Stephen Fulling, Paul Davis, and Bill Unruh, said that, thought about what would happen if you had an accelerating object and there was an acceleration horizon behind it. So this plane or spacecraft is accelerating to the right. It sees a Rindle horizon here beyond which information cannot get to it. That's the definition of a horizon. So again, we have one of these particle pairs. One is emitted in front of the horizon, one goes behind. The one that goes behind is lost from the point of view of the accelerating object, and the other one is able to become real, and this is now called Unruh radiation, or more completely, Fulling-Davis Unruh radiation. And this is a thermal kind of radiation, so it's as if the accelerating object sees a hot thermal bath surrounding it. And it's very strange because if an object is in the same space but is unaccelerating, it will not see this thermal bath. So that's Unruh radiation. So what I've done is I've modeled inertia using this Unruh radiation. So this shows the model. This object, this black ball here, is accelerating to the right, as shown by the purple arrow. And it sees Unruh radiation, which I've tried to show with this red sort of thermal radiation here. And this Unruh radiation also has wavelengths associated with it that I've tried to show with these red waves. So that's okay on this side of the particle, but on the other side, it sees a horizon. So information from behind this horizon can't catch up with it. So we have a horizon. And a new assumption of quantized inertia is simply that this horizon can damp these Unruh waves, just like the ship and the dock. So this object here is like the ship and the horizon is like the dock. So we see this wave can exist between the particle and the horizon, but other wavelengths of wave could not. So in this area, we have less Unruh radiation, less allowed wavelengths. And so I've tried to represent that with a blue shading, representing a colder Unruh field. So what does this do to the particle? Well, it means that it has a lot of radiation hitting it from in front in a direction it's accelerating, but it has far less radiation hitting it from the other side. So it tends to be pushed back against whatever acceleration it has. And I managed to show in this paper in 2013, with a correction in 2016, where Jaume Gine corrected a factor of 2, that this looks just like what we know as inertial mass, or the phenomenon of inertia, which is just a phenomenon that damps whatever acceleration you have, tries to oppose it. Okay. And I should say that this Unruh radiation has now been confirmed by Lynch et al., who emailed me very excitedly to say that he'd done it. So they looked at positrons decelerating very rapidly in silicon crystals and saw radiation coming off, which had a spectrum exactly equal to the expected spectrum from Unruh radiation. So they published that in this paper in Physics Review D. So Unruh radiation has now been confirmed, at least by this test. But okay, so quantized inertia can model inertial mass as we understood it, but that's not the whole story, because something special happens at a low acceleration. If you have an object with an extremely low acceleration, the Rindle horizon moves very far off, because it's quite easy for any any information in this area to catch up with a very slowly accelerating object. So the Ventura horizon goes further and further away until eventually it will be as far off as the cosmic horizon, which is the horizon beyond which we can't see. So this also constitutes a horizon. It's very far away, 10 to the 26 meters away, but it does exist, and we can't see beyond it in principle. Now, at this point, with this very low acceleration, the mechanism I proposed for inertial mass disappears, because there's now no asymmetry in the unruh radiation around the object. So you can see the unruh radiation can no longer push on the object. So the prediction of this model, a very simple formula when you work it out, is that the inertial mass decreases in a new way for very low accelerations. And I published this part of the theory back in 2007 in this paper in M and RAS. But this is exactly what is needed for astrophysics, because galaxies, this is the Andromeda galaxy, at their very edge, the stars in these galaxies orbit far too fast. So when they do the calculations, the inertial forces, or the centrifugal forces, if you like, should be enough to send the edge stars drifting off into space, because they're not able to be held in by the small amount of matter that we can see lit up in the galaxy. So of course, the standard thing is to add dark matter to the galaxy to keep these stars in at the edge. But quantized inertia solves this problem, because at the edge, the stars have an incredibly low acceleration. So quantized inertia predicts that they lose their inertial mass, a certain amount of their inertial mass. And it turns out that this reduces the centrifugal force by exactly the amount needed, so that it now balances the gravity from the matter we can see in the galaxy. And quantized inertia does this without any adjustment at all. And it works perfectly. And I published 2 papers, this one in 2012 and this one in 2017, to show that. Okay. So just to emphasize this point, in the center of galaxies, the acceleration is quite high. So the unruh waves are quite short, as shown here. As you go out to larger radii, the acceleration is reduced, so the unruh waves get longer. But at the exact radius where the unruh waves are the same size as the Hubble horizon and can therefore be damped by it, that's exactly where galaxies start to deviate from Newtonian behavior. So this is a very direct proof that the galaxy rotation problem is due to quantized inertia and unruh radiation, because no other theory can predict this cutoff here. Okay. So the great thing is that if we can if this represents a new understanding of inertial mass, and of course I think it does, then we can control inertial mass to make things move. So normally, in order to launch something into space, you need a rocket and you need a chemical reaction to fire hot gases downwards so that the conservation momentum makes the rockets move up. This is very dangerous and requires a lot of high-tech engineering and accuracy, and also a lot of heavy fuel. So what I'm proposing is instead that we have, obviously, that we use quantized inertia. And to do that, you need a very highly accelerated core. So I've represented that in this schematic as just a circle with an arrow, implying that there's something accelerating very rapidly inside this core here. So the prediction is that if you accelerate this core rapidly enough, the unruh waves will become short enough, as shown here, to be damped by material that we can manufacture, such as simply metal plates or metamaterials, but in the simplest form, metal plates. So this means that if you have this core and you put a metal plate above it, that will damp the unruh waves that are hitting the object from above, but it won't damp the unruh waves that are hitting it from below, so it will force it upwards. So this is a new way to move objects without the need for expelling propellant. You still need energy to accelerate whatever is accelerating inside here, but you don't need propellant. So it's a propellantless thruster. So one example of this kind of thing would be the M drive, which I became very interested in around about just soon after Scheuer showed it. So in 2008, Scheuer showed that a tapered microwave cavity, so something that looks like this, a cylindrical cavity with one wide end and a narrow end, will move towards its narrow end if there are microwaves resonating within it. And I managed to show that quantized inertia predicts this pretty well. So it's all to do with conservation of momentum. So if you imagine a microwave photon moving to the left, it's going to move from a region, this wide end, where more honor waves are allowed. So I've shown this with the yellowish reddish tinge there, to this narrow end where fewer honor waves are allowed. So that means its inertial mass is going to decline as it goes towards the left. And then when it comes back again, when it goes towards the right, its inertial mass is going to go up. So this means that there's a shift of momentum of inertial mass from the narrow end to the wide end. And in order to conserve momentum, the cavity itself has to move to the narrow end. And when you do the calculations, you see that the thrusts are very similar to the ones seen by Scheuer and other people who have done tests. So I've shown this on a plot here. So the x-axis is a thrust predicted by quantized inertia. I used to call it MISC. It's now quantized inertia in millinewtons, and the observed thrust up the y-axis. And if the theory worked, everything would be along or near to the diagonal line. And you can see that for all the, I think, 11 M drive tests shown here, it's quite successful. It's quite close to the line, and in fact, it also requires a modeling of where the dielectric is. M drives sometimes have dielectrics in them at the narrow end or the wide end, and that does make a difference, because if you include that detail, you get the black data here, and if you don't, you get the empty squares, which are further from the line. So the dielectric is important. Okay, so I published that in EPL in this paper here. Okay, so at this point, DARPA got into contact, and I applied for funding, and I got $1.3 million to demonstrate scalable thrust from QI in the lab. And we now have done that in several labs. Well, I say we, my Plymouth lab, but also other labs around the world. And a crucial advance was made by these two guys, Frank Becker and Anke Batt, who read my papers just about when this project was beginning, and they thought they'd try a capacitor setup. So a capacitor has a cathode and an anode and a dielectric between them, and they charge up to 5 kilovolts, for example, until such time as electrons start to tunnel across the gap from the cathode to the anode. And as Becker and Batt pointed out, this is an extremely high acceleration, one of the highest we can make. So this is a good candidate for a horizon drive. So they tried it. They put a capacitor on a digital scale. They charged it up to 5 kilovolts. They had a leakage current across the capacitor of about 10 microamps. And they saw a thrust. They saw a force upwards, which was very interesting. So this shows the data. So along the x-axis, this shows the separation between the plates. So a very wide separation, 120 micron here, down to about 10 micron down here. And the black diamonds show the thrust that they saw. So you can see that the thrust increases exponentially as you decrease the separation, up to a value of about 6 millinewtons down here. And quantized inertia predicts the force should follow this formula here. So the force is equal to a number. Now, this number is not a tuned number. This is simply equal to, contains things like pi, the mass of the electron and the charge of the electron, times the leakage current in the capacitor times the area of the plates divided by the separation squared. And if you apply the theory, you get the squares here, which agree with the data. So I described that in a paper here on ResearchGate. So it works very well. So the reason it works is as follows. So imagine you have an electron, which is shown here, accelerating to the right. Now, normally in quantized inertia, there will be a lot of underworld radiation in front of the electron and less behind because it's been damped by this horizon. So you get the red and the blue here. This underworld gradient pushes back on the electron, giving it its inertial mass. But in the case of an electron accelerating inside the capacitor, as shown here, it's different because the capacitor plates also damp the underworld radiation pretty well. So we get a blue area here and a blue area between the plates. This means that there is no longer any underworld gradient to give the electron its inertial mass, or I should say less underworld gradient to give it an inertial mass. So the electron's inertial mass will decrease. And to conserve momentum, the plates have to move towards the right. So for the maths of this, you could see the paper on ResearchGate here. But I should say that this intuitive understanding I've improved in the past few weeks. So it may differ from some things I've said before slightly, but the maths still applies in the same way. Okay. So after that, a very forward-thinking company, Ivo Limited in Virginia, USA, decided to try to confirm this. So in liaison with myself and Becker and Batts, they did many tests. Excuse me. And instead of using a digital balance to avoid artifacts, they used a pendulum. So they put a capacitor on a pendulum like this, and they charged it up, and they watched the pendulum move. And they also tried this in a vacuum chamber at E-Labs in Fredericksburg, Virginia. So the vacuum chamber is shown here on the right, and these are their plates. They're capacitor plates, and you can see they've stacked them to produce more force. And also they had a very good innovation, which I can't describe, but they used a better dielectric. The dielectric that was used by Becker and Batt was a plastic, Kapton, or PTFE. The Ivo used a far more robust dielectric. So that meant that the capacitors last much longer and are far less intermittent in their behavior. Okay, so their results agreed very well with quantized inertia. So this graph shows the voltage along the x-axis and the thrust they saw along the y-axis for one case, and the blue represents the predicted thrust and the black line represents the observed thrust. So it agrees quite well with the same formula here for this particular case. So it's possible to discount many of the artifacts people might suggest could be causing this. For example, could it be an electrostatic interaction with the environment? Well, this is ruled out because they try to control with a wide 60 micron separation, and there was no thrust. So iron wind, it can't be the iron wind because they were trying it in a vacuum chamber. I've calculated the effect of the Earth's magnetic field, which is far too small. It's about 0.2 micronewtons in this case. Thermal expansion, could it be that? Well, I've calculated that too, and this would only, I think, cause less than a micrometer expansion, but the pendulum movement was about 150 micron. and for other reasons as well, we can discount thermal expansion. And other things can be discounted too. Okay, so I also managed to divert some DARPA money to Plymouth to set up a lab to also try to confirm this. So we set up a system like this. We had a digital balance here. We had a tower to separate the capacitor from the balance to avoid any electrostatic interaction. We used Kapton for the dielectric. We had a high potential tester, Vitrec V71, to produce a high voltages. We put in the current through Gallon stand to try to decouple the capacitor from the external environment so it could move freely without friction or things like wire. The expansion of the wires should be cut out as well. For the capacitor, we were using aluminium foil, separation of about 8 or 16 micron. We varied it a bit. The area of our plates was typically 4 by 4 centimeters on the side, and our leakage currents were rather smaller than Becker and Batt, so about 0.1 microamp, less than they tended to get a few microamps out. So our thrusts are smaller, but we did see some thrusts. So this is our actual lab. This was my chief engineer, Richard Arundel, setting it up. It was done as part of his PhD, and we performed over 200 tests in a few months and slowly improved our system. You can see a few YouTubes of our work here. Curve shows the rate of change of mass of the capacitor. And so it's showing that what we tended to do was as I'll explain in a minute, we had to heat the capacitors because the effect tends to occur above about 50 degrees Celsius. So the capacitors then tended to cool down and lose buoyancy. So there was a slow loss of buoyancy in this black curve. But the orange curve shows that when we applied a voltage to the capacitor, so from about 2 kilovolts to about 4 kilovolts, increasing here, the theory predicts that we should get a drop, and that predicted drop is shown by the blue line here. And you can probably see that most of these, well, 3 out of 5, are represented in the black curve. So the weight was supposed to drop, and it did here. It was supposed to drop, and it didn't here, but it was supposed to drop here, and it did, and also here as well. So that was one of our early tests. As we got more sophisticated, we were able to isolate different effects. So, for example, this graph here shows the effect of heating on thrust. So on the x-axis is the predicted change of mass. On the y-axis is the observed one. And when we didn't heat the capacitors, it was the prediction was way off. But when we did heat the capacitors to above 50 degrees C, the result was pretty good. So this shows that heating is important, and it's thought that heating reduces the work function of the metal. That's known, and enhances the Fowler-Nordheim tunneling that's needed for the thrust effect. So that produces a very high acceleration of electrons as they tunnel across the capacitor gap. Okay, so 5, well, I say 5, it's really only 4, but there was one done by Honda quite a few years ago, back in 2008, where they had a similar setup. And they observed a thrust in their capacitor, which was slightly different to the ones we're using, of about 14 millinewtons. And when you apply quantized inertia, you try to predict what they would see, you get between 10 and 19 millinewtons. So that fits. Becker and Batt's result was about 6 millinewtons, and QI quantized inertia predicts that well. Ivo as well. They had various results, but this particular one, and most of them agreed with what quantized inertia was predicting. And our test in our lab, we got 0.25 millinewtons. We observed that, and quantized inertia predicted exactly that. And then there's another team, I should say. I'm not allowed to tell you their company name, but they're from Italy, and they had a very nice setup in a vacuum. And they saw almost 0.1 millinewtons, and quantized inertia predicts 0.1 millinewtons. So we've submitted a paper on these experimental tests, which I'm willing to send to people if they want to see it. You just need to ask. Okay. So then IVO, this company led by Richard Mansell, they went one better, and they actually launched a test into space. They were using a 3U CubeSat of Rogue Space Systems, launched by SpaceX, Falcon 9, and they had 2 quantum drives on board of their own design. So in their lab, they actually had thrusts up to about 52 millinewtons, but they had to curb that to launch them into space on a CubeSat. So their thrusters were about 0.25 millinewtons and one of 0.65, a bit smaller. But the idea here was to try both of the thrusters separately and see if the resulting hoped for motion in the satellite would agree with the combination or which thruster was being used. Unfortunately, the satellite was lost before the test could be performed. It was lost sometime in mid-January. So we don't have any data from that, but they do intend to launch again, perhaps early next year. Okay. So what does this kind of thruster mean? Well, at the moment, satellites use ion drives. So, for example, the Dawn probe to the asteroid Ceres, or minor planet Ceres, its ion drive produced 90 millinewtons. But it had a weight of about half a ton, because it had to carry all its propellant, and it needed 2 kilowatts of power. But it produced 27 meters per second in 1 or 2 days. In our lab at Plymouth, we've seen about 0.25 millinewtons, which seems much less. But a CubeSat with such a thruster would have a much lower weight, only about 3 kilograms, because it wouldn't have to carry propellant, and it would only need about 1 watt instead of 2,000 or so. And its performance would be comparable without the need for fuel. It would need energy, of course, to accelerate electrons, but that can be gained from solar panels. Okay. So the applications, I guess, initially are quite obvious. Satellite station keeping is one. Satellites would be lighter to launch, and they would last longer, and they would be silent. No fuel, no exhaust. So further down the line, theoretically, I can predict that this kind of technology would produce a lot more than I've described so far. I think it would be possible to manufacture nanomaterials that self-thrust, so be able to build structures that hover or things that take off with the horizon drive. Another unique characteristic of this drive is that there be no whiplash, because when you accelerate a spacecraft by making a gradient in the Unruh field, then that gradient applies to every object in the spacecraft at the same rate as it applies to the spacecraft. So you won't be thrown around by large accelerations. I think there are ways of getting energy from the vacuum as well, but I won't go into that today. Interplanetary trips become a lot easier and cheaper, and this kind of drive would make interstellar trips possible in a human lifetime, as I'll describe here. So I think if you built a probe like this, so you've got a very long cylinder with a shield, one end, an RTG to produce power, 1,000 stacked horizon drives here, capacitors. Then, according to the theory, this will be able to get to Proxima Centauri in 10 or 15 years, something like that. Normally, this is impossible, because in order to get up to half the speed of light, you would need an awful lot of fuel, which would be heavy. So this actually precludes getting to Proxima Centauri in the human lifetime. But with this kind of horizon drive, you wouldn't need fuel. So you will be able to do it. I think you could accelerate to about half the speed of light in about 2 years. You'd have traveled 0.4 light years. Then you cruise for a bit and then decelerate symmetrically at the other end. And you could decelerate by simply reversing the polarity on the capacitor plates. That would be quite easy to do. So time to Proxima 10 or 15 years, something like that, depending on the design. Okay. And this is something that was rendered a few days ago by Kelvin Long. This is what a QI Horizon Drive probe might look like when it arrives at Proxima b, the planet of Proxima Centauri. It would be nice to see that. Okay, so just to emphasize that what I'm talking about, the theory I'm talking about, quantized inertia, has been extremely well tested by me over the past 18 years with astrophysics, and by me and others in the lab over the past 4 years or so. And this plot lists 29 anomalies, if you like, or phenomena that quantized inertia predicts that standard physics cannot. So there are things like the cosmic acceleration, the galaxy rotation problem is solved. There's a new explanation for inertia. The theory also predicts the value of G. So we don't actually need G anymore. You can replace it with things like the cosmic diameter. It explains wide binary orbits, spacecraft anomalies, things like the M drive, these capacitor thrusters, and maybe things like cold fusion as well. I've published peer-reviewed papers describing most of these and showing how quantized inertia predicts them. Okay, so to conclude, quantized inertia promises a great leap forward, both in it updates physics, makes it much better, in my opinion, and also represents real advances in technology. It's the first explanation for inertia that's been proposed. It predicts a minimum cosmic acceleration, which gets me into trouble because it very, very slightly violates Newton's first law, which states that things keep going in a straight line until you push on them. But this cosmic acceleration is extremely small, 10 to the minus 10 meters per second. And when you do have this minimum cosmic acceleration, you predict galaxies and everything else much better than standard physics does. It's been validated in space with galaxy rotation, etc. 4 labs have seen QI-like thrust, and there has been the IVO space test. But as I said, the spacecraft failed before the test could be done. So next steps for me, I'm trying to set up what might be called a Horizon Institute. I want to obviously continue to work on the QI theory, enhance the thrust, work on the energy applications, and then try to somehow work out how to perform interplanetary and interstellar missions, because I think they're possible and we should be doing them. Okay, if you want to email me, my emails are up here. If you want to buy my books, they're listed here. And thank you very much for listening, and I can now take questions.
Mike, thank you. Thank you. That's wonderful. So yeah, and guys, just take note of Mike's email. And I think, Mike, I think everybody has that, and probably from your website too. So what I want to do is take down the presentation and bring in everybody and do questions there. Let me take down the slideshow. I'll bring everybody in. But before anything else, I see Jared coming over there. Let's give Dr. Mike McCullough an enormous hand. And Mike, you've been making headlines too because of the IVO thing. So that's amazing. I mean, your work is getting traction. It is changing minds and it is moving forward. So that's wonderful. And thank you for coming today too. I can hear you're still coughing a little bit.
Yes.
I do hope that you feel better, in the next few weeks as we move into spring. So
It's been a terrible winter here. We haven't seen much of the sun in Britain at all. So
I'm in
everybody's
Seattle.
coughing.
Trust me. Yeah, we got the same thing going on here. It's only 55. My kid's outside sunbathing. She's like, it's so warm. I'm like, no, not really. So, well, guys, do you have any questions for Jared? Go for it. We'll go Jared and then Drew.
Dr. Mullick, outstanding presentation. I just had one question. Are there any astronomical observations that you've yet to see that you'd like to see that might help support QI?
Yes, the first one I could think of would be the bullet cluster. I think you've heard of that one, which is usually taken as evidence for dark matter. But if you look at where they have to put the dark matter, they put it along the spin axis of the bullet cluster. And that's something that quantized inertia predicts, that there should be a loss of inertial mass for objects crossing over spin axes. So light should be bent close to the spin axes of objects. So it should appear that there is matter there. But there's actually not. So I think it'll work, but I haven't tried it.
Thank you.
Awesome. Thank you. And then let me see. I think Drew, you had a question?
Yes, Dr. McCullough. I've run the same basic test that you're setting up your lab in Plymouth with the capacitor thing and the digital balances, and I got to tell you, there's dozens of ways that test is seriously flawed. But the question I have is, how did you separate the power supply current from any tunneling current? I'm just curious how you measured your specific tunneling current.
Well, the Vitrec, the high potential tester we used measures the draw on power of the system. So we measured it using that.
Yeah, that means that it's measuring the draw on the power supply.
Yes.
Did you run any of these experiments where you didn't have your test article connected, but you did have your power supply giving out its draw?
Yes,
Because
we also
I've done that.
Yeah, earlier on I had a postdoc earlier on who was directly measuring the current passing between the plates. So we worked out an empirical formula to also predict what the current was, and that agreed with what the potential tester was testing us later on. But I'm perfectly willing to admit that there may be some other things going on. I can send you my paper if you want, and you can have a look.
Sure. Yeah, I'll email you offline. Thank you.
Yeah,
Awesome. Jared, go for it, sir. Oh, Jared.
Let Dan go first.
Oh, Dan, go for it. I'm sorry, I didn't see your hand up.
No, I let Jared go. I have a couple questions, so Jared can go.
Oh,
All right. I just had one other question. One of the experiments that you sent over to Dr. Tamar, I loved the idea of it, but the negative results seemed a little weird to me. It was the fiber optic loop that you had that was like shaped like an egg, and it was like 3,000 turns of fiber optic. Any ideas on if that could be improved, why that didn't work?
Yes, if you look at my paper on ResearchGate, I think I put another one up there recently. There's a price you have to pay for using photons instead of electrons. They're obviously far lighter than electrons, and so when I looked at the theory again, I realized that yes, you would get a null result, a much smaller result than I'd first expected from the fiber optic approach. So that's a theoretical mistake that I made in my expectations. So
Could it be improved?
Yes. So it's interesting that in order to counteract the fact that the photons are so much lighter, they have so much less momentum, you have to put in a lot more power. And that is actually done in the M drive. So I think you could still have these light-based mechanisms, QI drives, but you just need a lot more power, comparable to the power put into the M drive, which is about a kilowatt or so.
Thank you.
Awesome. And then Dan, go for it, sir.
Yeah, so I had 4 remaining questions, and I know we're getting short on time, so I'll try to go through them quick. So I guess building first off Jared's comment on potential cosmological predictions that your model might make, I'd be really curious to see what your model has to say about the cosmological coupling of black hole masses to the cosmic event horizon. Is that something you've played with at all?
Well, I have a sort of principle that I work by, that I try to only predict objects that are well observed. So at the moment, I don't like to look at things like black holes, and I'm not so keen on a cosmic microwave background because they're quite either indirect observations or they haven't been well observed yet.
Yeah, the reason I'm asking, there's been some recent James Webb observations on early black hole masses that don't exactly line up with certain models. So I was just curious if yours might explain that. So instead of getting hung up on that, does your my second question, does your what does your model say about things like a Kuiper drive?
Okay, so one of the reasons I produce quantized inertia is because I don't like the bent space physics that's used in general relativity. I do prefer the Einstein's earlier version of general relativity from 1912, where he had variable speed of light, and he treated space as almost like having a medium with a refractive index. That fits much better with what I'm doing. So instead of having a bent space that you can never directly observe, I'm trying to rewrite it so that you have everything is produced by motion is produced by gradients and unruh radiation, and unruh radiation can be directly seen.
Okay.
As it has been recently. So it's directly testable then. So some similar predictions to the Alcubierre drive. You can tease the speed of light by producing a horizon around a ship. That's a prediction, but I don't do it using bent space. I do it with horizons instead. So I published a paper on that as well.
Oh,
Okay.
Dave, go for it. Oh, sorry.
Thank you. That
Oh, well, let's go to David because I think Dan's connection just cut out. So,
yeah, you didn't touch on your one paper or the superluminal travel from quantized inertia.
Dan, your connection is cutting out.
Yeah, it was hard to hear that. All right. Well, yeah, thanks for your talk, Dr. McCullough. I was curious.
No, is that better? I just closed my tab.
Oh, yeah. Let me go to David really quick, though. Sorry.
So I was curious if quantized inertia could help describe how the graviflyer works. But I'm also going to assume that you don't know what that device is, and I'll just mention that Mike Gamble is going to give a talk on it later. And then rather than focusing on the graviflyer, how would you say that quantized inertia helps describe the results of Podkletnov?
Yes. So, yeah, Podkletnov is still a very controversial effect. Hasn't been reproduced, but it hasn't been done properly either by anybody else. I think what's happening there is because Podkletnov had 2 layers of superconductors which have different grain sizes above and below. So the acceleration of the disk produced short Unruh waves, and the difference in grade sizes then produces a gradient in the Unruh field, which produced a force on and around the disk. So that's the way I model it with quantized inertia. And I published a paper, and I got a similar thrust to the one that was seen. So yeah.
Okay, thanks. Yeah, I'll
Awesome.
have to look more into that.
Thank you. Let me see if I can bring Dan back. Dan, connection.
Sorry about that.
Oh no worries,
so
no worries.
My last two questions were about your one paper, superluminal travel from quantized inertia. I'm surprised you didn't touch on that at all in your talk. And then secondly, just before my connection goes again, is there any particular interpretation of QM that your model agrees or disagrees with?
QM.
Quantum mechanics.
Well, closest I've got to that is publishing a paper about the EPR paradox. Yes, I don't know enough about the interpretations of quantum mechanics to talk about that really.
Okay.
And the reason I don't talk much about the superluminal paper is because shortly after I published it, I changed my mind about it. But looking at it more recently, I think maybe it's okay actually. So I'm kind of dithering over it.
I think it's okay too. So keep with that hunch.
Okay. Well. Yeah.
Okay,
Thanks.
we have about
thanks
2 minutes. We have about 2 minutes left. So, yeah. Does anybody else have a Drew? Go for it.
Yeah, just one more quick question. If you're running your experiment and you're getting your tunneling current and you cut off the high voltage power, do you expect the thrust to dissipate or to remain?
Yes. Yeah, it should go pretty quickly, and it did in our experience.
Okay, so if the thrust remained after you cut off your power, there would be something else going on.
Yes, that's right. Yeah.
Yeah, I assure you there's something else going on. Thanks.
Wonderful. Okay.
Well, yes,
Well,
you
thank
might
you.
be right, but I should send you my paper.
Yeah, and we are just about there. Mike, thank you again. Thank you again. And I know that you are recovering from a cold. I appreciate your spending the time with this. I do not want to keep you on any longer than absolutely necessary, but again, it is truly an honor to have you present at APEC. And the quantized inertia, the work that you're doing is this is making headlines, right? And so it's absolutely wonderful, and if anyone deserves the positive attention, it is you. You have done so much hard work for so long on this. So guys, let's do this. Let's put our hands together one more time for Dr. Mike McCullough. Mike, thank you again so much. I would love to have you back in the future, but right now, take some time, get some good rest, and thank you again so much for presenting for us today.
Okay. Well, thanks for the questions.
Absolutely. Okay, I'm going to remove everybody from the studio for right now, and I'm going to bring in, let me see, Dr. Nathan Innan. Nathan, welcome, sir. And you were doing a presentation on, let me see, linearized general relativity, classical coupling of EM and gravity. And, I'm not even going to try and read the description. This is like the long form technical description. So that's on the website. And it looks like you were muted. Let me see if I can. Oh, it looks like you have to unmute yourself. There we go.
You hear me okay?
Yeah. And I'm going to bring your paper in. And so
Sure.
what I will do, thank you so much for presenting for us. So I know that you've been working with Dr. Sarfati and several other folks. And so and I think Raymond Chow also, right?
That's right. Yeah.
Okay. Well,
Yeah,
thank
in
you.
fact,
I'm going to remove myself from the studio, but I will be here if you need me, and take it away. And thank you yet again, sir.
That's perfect. Thank you so much. In fact, I'm going to go ahead and share my screen, if I may, so that I can use the slideshow that I have already launched on my computer here. So let me know if you're able to to see my screen. I just hit share. Do you see me okay?
Yeah,
So you should
there we go.
see, here's our title slide. Do you see the title slide there?
Yeah. Now it is a little bit small, but that's okay. I think people will be able to read it. And yeah, that
Oh.
looks fine. So that
Oh,
looks fine.
I had to fire it. Great, great. All right. So yeah, thank you so much, Tim, for inviting me. Thank you for the APEC community for allowing me to share this research. This is my first time sharing ever with the APEC community, although I have had affiliation with a number of individuals, namely Dr. Raymond Chow was my PhD advisor. Dr. Jack Sarfati is somebody who I've been corresponding with and working on some research on lately. And Dr. Jim Woodward is also someone I've known for quite a number of years. And Dr. Jose Rodau. I think there's probably other people I've met as well who are connected to APEC. So for myself, my name is Dr. Nader or Nathan Enan. I commonly go by Nathan. I teach at Clovis College, and I'm affiliated with Dr. Raymond Chow at UC Merced and researchers there. And as of late, I've also been affiliated with Texas Space, a company that's basically forging the frontiers of research in the very areas that we talk about at APEC, things pertaining to obviously gravitational physics, propulsion, gravitational wave communication, and all the related topics. So this content that I have here is something I have worked on for a number of years. There's a variety of papers that I published with various colleagues who I'll mention, but that I'm also trying to connect with Texas Space in hopes that we can actually get this into technology that actually affects our life eventually. That's the hope. So I'd like to mention the research topics I work on just as a little sort of like mini advertisement in hopes that I could be invited back again, because I do love everything APEC is doing. So what I'm going to focus on today is classical coupling of electromagnetism and gravity, just because I thought that would lay a nice framework for other topics I may have an opportunity to share in the future. So I'm going to focus mainly on the idea of gravitational Faraday-like flux rules and their applications, and some new formulations of gravito-electromagnetism that can basically provide like tools, like a framework for a variety of applications that I'll mention. Now, these other items, there's a bunch of them, a plethora of them, I'm not going to manage to get to today, but I just want to kind of put the cards on the table that they're there for future occasion. We've been looking at the transduction between electromagnetic and gravitational waves, methods of extracting energy momentum from gravitational fields, and then going into the quantum regime. I look a lot at the London and Ginzburg-Landau theory and curved spacetime. My focus has been very much on superconductors in my research. Gravitomagnetic Meissner effect, quantization of gravitomagnetic flux by a superconducting ring. And as of lately, I've been looking at correspondence principle applied to photons and gravitons. That's something I'm doing with some students at the college. Now, this category here, gravitational expulsion, reflection, and transduction, is also a topic that I'll touch on a little bit today, particularly how normal conductors and superconductors are expected to interact with gravitational waves. There is something called a charge separation effect that we've written on, electromagnetically induced gravitational wave reflection. That's something in particular we really want to get going with Texas Space and hopefully even get patented and put into some technology. Gravitational waveguide modes, gravitational radiation reaction force, oscillation and deformation of levitated superconducting slab, and then quantum effects associated with gravitational waves, like graviton-photon conversion, gravitationally induced phonon-Casimir effect, and just a gravitational Casimir effect in general. And the hope would be at one day producing a gazer. I imagine this community is familiar with the gazer. It's a gravitational laser. I also look at the Aharonov-Bohm effects, fluctuation dissipation theorem, and coupling gravitational field of the expanding universe to a local system. So I worked with Dr. Lance Williams extensively on that topic. More recently, I've been working on dark energy, dark matter, and the cosmological constant problem. So our last speaker talked about the quantum space-time foam, and Unruh and Hawking effects and so forth. All right, so I'm going to kick it off with some background just so that kind of you know what the mathematics is showing that I'm laying down. Kind of like the flat space-time metric here, the signature -1, +1, 1, 1. Writing down the metric in terms of a flat space-time plus a perturbation. And as most of us probably know, the perturbation basically represents the distortion of space-time, stretching, compressing, distorting of various sorts. So this is my GR in a nutshell. I've taught GR here and there a little bit, and this is my final slide. If my students understand this, I'd like to believe they understand GR. So we've got the metric, the Riemann tensor, the Ricci tensor, the Ricci scalar. We construct the Einstein tensor. We've got our stress tensor. Put it all together with the cosmological constant, and voila, you've cooked up GR. As I said, in a nutshell, probably takes a little more to learn GR than this slide, but hopefully you get the idea. Now, if we look at linearized GR, so a small perturbation, so h mu is much less than 1, commonly we define the trace-reversed perturbation as it's shown there on the slide. And oftentimes a gravitoscalar and a gravitovector potential is defined in terms of the 0, component and the 0I component of the perturbation. And I'll mention, by the way, that this row here with the bars is in terms of the trace-reverse perturbation. The row below is the same physics, but just in terms of the non-trace-reverse perturbation. The reason I mention that is because oftentimes in linearized GR, as I've seen in the literature, authors tend to believe that gravity could be reduced to a vector theory because it appears like I just have a 4 vector here, 1 scalar and 3 components of a 3 vector. But you got to keep in mind that's in the trace-reversed perturbation. So if we go to the regular perturbation, this still is a tensor theory. And the reason I'm emphasizing this here is because one of the main points I'm going to make is that gravitational waves are tensor waves. And one of the common errors that I've noticed in the literature that I've spent some time correcting is the idea of gravitational waves being vector waves. So we're going to spend some time on that. So do notice that this is a tensor theory, even in linearized GR. And we can write down a so-called gravitoelectric field and gravitomagnetic field, which are written basically purely by analogy with electromagnetism. And I would argue that's pretty much all that's going on here is using E&M as a sort of basis for defining these fields. Now, granted, they are measurable in the sense that we know the gravitoelectric contains Newton's gravity. It's holding our feet to the ground. The gravitomagnetic field is understood to be caused by mass currents and would cause deflection of particles by the good old right-hand rule, as I raise my left hand. Earth drags space-time in a circular type motion. Sometimes this is called frame dragging. And it's even been measured by gravity probe B, detects deviations in line of sight towards the stars. So they are real physical phenomena, but as I'm going to show, there's limitations to this formulation, and I'm going to propose a superior formulation that doesn't have the same limitations. So again, I'm going to kind of move right down quickly through linearized GR. We got our Christoffel symbols. In the linearized regime, we can ignore 2 of the contributions to the Riemann tensor that are quadratic in the Christoffel symbol. We can write down the Riemann tensor in terms of the perturbation, the Ricci tensor, go on to the Ricci scalar, and we can write down the Einstein tensor in a linearized GR regime. Now, it's helpful also to remind ourselves that we've got the option of coordinate transformations. And in linearized GR, usually a linear coordinate transformation is employed. And the metric perturbation then transforms accordingly. So that C mu is going to play an important role. Keep that in mind. It's basically a shift of our coordinates. Nothing physical, just shifting coordinates around. So in light of that, it's often been noticed that that transformation of the perturbation looks a lot like the transformation for the electromagnetic 4 potential. And so it's common to choose the so-called harmonic gauge because it's very analogous to the Lorentz gauge in electromagnetism. And furthermore, the Einstein equation becomes a wave equation. After all, you just saw the wave, right? So it's a wave equation. But you know, in all seriousness, it's a wave equation, just like Maxwell's equation in Lorentz gauge. So that's very suggestive that gravity could be written in a format similar to electromagnetism, at least in linearized regime. So you can even write down like a gravitational 4 potential. I remind you, it's not a real 4 vector. It doesn't transform as a 4 vector. That could be shown. Oftentimes we use the ideal fluid stress tensor and we reduce it to just relativistic dust. Or excuse me, in this context, I'm going to stick with non-relativistic dust because that's commonly where the mass current J is defined, and then the stress is set to 0. And that's because Maxwell's equations, when we write them down and for electromagnetism, we only see a charge density and a current density, or in typical like undergrad electromagnetism. So we could even define like a mass 4 current and write down a Maxwell-like field equation that looks a lot like electromagnetism in Lorentz gauge. Now, here's where we have to be careful. Okay, here's where the red flags rise. A Green's function solution to the Einstein field equation shows us that each component of the perturbation is proportional to each component of the stress, which means that if we are taking a non-relativistic approximation and considering the Tij stress to be approximately 0, then in a sense, we are also showing that Hij bar is effectively 0, because that very last relationship there, showing that Hij is related to H00 by V over C quantity squared. So if we go to a non-relativistic approximation, Hij bar is gone. Now, what that means is because we're using the harmonic gauge, if you expand that harmonic gauge, as I've shown at the top there with the arrow, and you set Hij to 0, then that shows the time derivative of the H0i, the gravito vector potential, is also 0, which means you don't have a time derivative of the gravito vector potential. So the gravito electric field is truncated down if we approximate consistently to just the Newtonian field. And what that does furthermore is if you take a curl, you don't have a gravito Faraday law in this approximation. So furthermore, we're going to want to write down the equation of motion as well. So we start with the geodesic equation of motion. I've defined the 4 position or 4 displacement, the 4 velocity, and the 4 acceleration in the usual manner. If we write down the linearized Christoffel symbol and we make use of the metric perturbation that I already defined earlier, and I did define one more quantity, this capital H is just the trace, the spatial trace of your Hij. If you do that, here's where you arrive. These are the non-relativistic gravito-electromagnetic equations in harmonic gauge. Now, notice, you got your Gauss law, you got your Ampere law, you got your usual magnetic Gauss, like no magnetic monopole type idea, but no Faraday, right? And furthermore, in your Lorentz-like force, there are terms there that are not Lorentz-like. First of all, you got this factor of 4. Some people think it's kind of pesky because it breaks the similarity to the Lorentz force, but it comes out naturally. If you try to redefine your fields to absorb it and eliminate it, that 4 will pop up in your field equations. It's there. And then you've got these extra 2 terms that appear there as well. So this is just a highlight. We can't get true perfect electromagnetism form in linearized GR. Now, you'll notice the constants on the side there are defined in such a way as to get a gravito-electric permittivity and gravito-magnetic permeability so that we can make our equations Maxwell-like. Now, this is my naive gravito-electromagnetism slide to show that what you will find in a multitude of papers are a set of field equations that is identical to Maxwell's equations. Faraday is there, right? And the Lorentz-like force is truncated to just the electric and magnetic pieces. All the rest are thrown away because those don't look like Lorentz, so we don't like them. And the 4 is just dropped because we don't like that either. But I argue this never comes out of general relativity. And there's going to be some critical ramifications to that I'll elaborate on as well. Now, if you're interested in more details, I wrote a paper with my colleague, Dr. Lance Williams, called Maxwellian Mirages and General Relativity, where we go some of the nitty-gritty on this. But since then, we've also actually done some further work that I'd like to share, because you might ask, well, what if I keep everything relativistic? What's that going to look like? Well, let me answer that question. So let me define a few fields that are going to help us along the way throughout the rest of this talk, actually. I'm going to define an electric-like and magnetic-like gravito-electromagnetic tensor field. So it's this script E and this script B. And you notice they're very similar to the way we define the electric and magnetic fields in electromagnetism in terms of the vector potential, usually written as an A vector. In other words, the electric-like tensor field is a time derivative of Hij, and the magnetic-like tensor field is a curl of the Hij, but they're tensor fields. It will also be helpful to define one other vector field. I just called it S, not to be confused with my respected colleague, Dr. Sarfati, who has his own S field. It's not that. This is just the spatial derivative of Hij. And so you'll notice, interestingly, if you utilize the gauge condition, you'll find that the gravito-electric field can actually be written as a gradient of the scalar potential as usual, but it actually can have a second term that's really just this S vector field. You don't need a time derivative of the H vector anymore. And so now notice, it naturally follows that because of these two tensor field definitions, they satisfy a Faraday-like relationship. Because if you just take the curl of your gravito-electric, you'll find it's equal to the time derivative of your gravito-magnetic tensor fields. But also, interestingly, the Einstein equation that we saw earlier as a box operator of Hij, it's a wave equation, can be expanded out into what looks kind of like an Ampere tensor equation. You see how you have like a curl of magnetic on the left, you've got a source on the right, and you've got a time derivative of the electric on the right, and then you've got this extra term that kind of breaks the similarity, but still, interestingly, we got something Ampere-like. So in a nutshell, I would suggest this is the real set of gravito-electromagnetic equations if we're going to be in harmonic coordinates, harmonic gauge. This is like the full deal right here. And then, of course, you'll have the full equation of motion. So notice it's more complicated because you see here the electric piece has a relativistic correction. The magnetic piece pretty much stayed the same. But then you've got a ton of other terms all the way up to third order in particle velocity. So I am using little v for particle velocity, not to be confused with big V that I use for the velocity of sources. Okay, now you might say, great, we solved the problem. Well, interestingly, general relativity is such a rich subject that you have such a multitude of ways of expressing the same physics. So for instance, if we start back up at the Einstein field equation and we write it in terms of the regular perturbation, not trace reversed, but we use the trace reversed stress on the right, then we find that we're motivated to define the scalar and vector potentials a little bit different, just a little. So I put a tilde on them. And so you've got, again, a gravito-electric vector field, gravito-magnetic vector field. You got an S field, and you got these tensor fields again, but they all have tildes because they're all defined a little different. They're all defined in terms of just H, not H bar. And so it's kind of interesting to see what comes out. It turns out the field equations look a bit nastier. I mean, look at Gauss's law. It picked up like a second time derivative term, and the source is no longer just T00. 0. Ampere's law picked up another term, and the rest are just tensor equations, so they're going to probably look nasty no matter what you do. But interestingly, the force equation looks better. Look, you've got your electric term, magnetic term without the pesky 4. Granted, you still have some additional terms there, but actually there's less terms than you had before. So you did simplify the equation of motion, but at the expense of complicating the field equations, right? But the moral of the story here is that there's no one single set of gravito-electromagnetic equations, although I'll suggest that there's a set that is superior to these. So, but before I do that, I just want to show some cool ideas that come out of using the gravito-electromagnetic field equations, even in harmonic gauge. So you could recall that the electromagnetic EMF is essentially the line integral of the Lorentz force. And we know also that the Faraday flux rule tells us that the EMF is negative the time derivative of the magnetic flux. Now you can play a little game where you apply a product rule on that flux so that the first term has a time derivative of the field and the second term has a time derivative of the surface area, and break it up. And what you'll find is that you will come back to the line integral of the Lorentz force. So there's an interesting connection then between the line integral of the Lorentz force and the time derivative of the magnetic flux. Now, the idea then is, can we play the same game with gravity? So for instance, let's take the gravitational Lorentz force to first order in velocity, so we keep our sanity. We don't want to go all the way up to second or third order in particle velocity. So in other words, this would be non-relativistic particles, okay? And you take a line integral and call this a gravitational EMF on the left side there. Now, if you play that Faraday flux rule idea again, it tells us then basically that you could generate a gravitational EMF by a time-varying gravitomagnetic flux, those two red bubbles. So you might wonder, well, what does that mean? Okay, well, let me flesh this out a little bit more. Let's put both our theories into one, gravity and E&M. So gravity is the Christoffel symbol there. E&M is coming in through the strength tensor term. This is standard Lorentz force in curved spacetime. Now play that game I just mentioned with this whole shebang. So you've got the usual Lorentz force in blue, the gravitational, purely gravitational in red, and then you have this interesting new coupling that comes in the green that involves both electromagnetic and gravitational quantities together. And this is what I'm calling a coupling of electromagnetic and gravitational fields, which perhaps could lead to new gravitational induction effects that perhaps could be enhanced by strong electromagnetic fields. So in other words, if you could beef up your electric field and your magnetic field, then this green term might introduce new forces that we've never observed before, just an idea. So if you wish, you could write this as a total EMF, the electromagnetic EMF plus the purely gravitational EMF plus this coupling EMF between both gravity and E&M. So here are a couple like application concepts, like propulsion of a conducting ring via Earth's magnetic and gravitational fields. So like imagine, for instance, you drop a ring in Earth's fields. Now remember, of course, we know Earth has both a magnetic field and a gravitomagnetic field. So both fluxes would occur as that ring drops toward the Earth. And so there would indeed be this total EMF that would occur in the ring, including this green coupling between both gravity and electromagnetism together. So say, for instance, what if you drive some electromagnetic fields in that ring while it's moving in Earth's gravity? Then you could essentially control this green part here, where you're controlling it by the electromagnetic, by adjusting the electromagnetic fields, but the gravitational fields are introducing perhaps new directions or new thrusts that wouldn't otherwise be there, is kind of the idea. So it's kind of like the old jumping ring experiment. You know, I'm a college instructor, so, you know, I do fun experiments in the classroom, and we know the jumping ring. So this would be like a gravitationally enhanced or modified version of the jumping ring experiment, which might be a first step toward gravitational propulsion in some practical laboratory measurable way. Another application concept might be like a type of motor generator via a rotating conducting loop. Again, you see the same equation, and the idea, of course, is as the loop rotates, then you have a change in both magnetic and gravitomagnetic fields in there. And as a result, you might have effects that wouldn't otherwise exist. So those are just some cool ideas that are yet to be explored, maybe even experimentally at some stage in the game. We need to run numbers and kind of see where it takes us. Now, this is this model here comes from a paper that I recently wrote a couple of years ago. The idea was basically if you had a superconducting ring, and you introduced a gravitomagnetic field through it, then you could look at what forces could be produced in that ring as a result of the gravitomagnetic field passing through the ring. It turned out there was also a gravitationally induced Hall effect that you would have in there as well. Again, I go into the more details in the paper, so I won't spend time on that here. But I did find that it was interesting that there is already a system that exists in Japan, not meant for these experiments, but for other purposes. It's the world's largest flywheel power storage system using a superconducting magnet bearing. And it's got some pretty extreme parameters. It's 2 meters in diameter, weighs 4 tons, and is rotating at a maximum speed of 6,000 RPM. So personally, I would not want to be that guy standing next to it if it were running. I don't know if I trust that. But anyways, I did some calculations, and there's a potential that the gravitomagnetic field that thing is producing would be perhaps usable in an experiment for an actual laboratory measurement and manipulation of gravitomagnetic fields. So like I said, more details can be found in this paper if you're interested on superconductor Meissner effects for gravitoelectromagnetic fields in harmonic coordinates due to non-relativistic gravitational sources. Kind of a mouthful, but the reason why I wrote that long mouthful title is because I plan to have some follow-up papers where I'm going to look at cases where we're not in harmonic coordinates. Rather, we will be in coordinate invariant formulation, which is what I'm going to focus on mainly for the rest of this talk. And it will be for potentially relativistic sources versus here non-relativistic. So I was kind of anticipating that I'm going to publish other papers that will change this title, and I wanted the variation between the papers to be obvious. Okay, now I'd like to shift gears to gravitational waves because it's a personal favorite, and it's what I want to demonstrate is well described by an alternative form of gravitoelectromagnetism. So those familiar with gravitational waves, you'll know that you got your plus and cross polarizations. This is me just doing a little animation of like how to kind of picture maybe like a standing gravitational wave if it were to exist. And so plus and cross polarization are well known in standard textbook general relativity as the polarization states that are possible for gravitational waves. Now, here is where confusion starts to come about. Again, I'd like to provide some clarification here. Oftentimes, there's assumptions made that the gravitoelectric field and the gravitomagnetic field are responsible for gravitational waves. But it's going to be demonstrated here that that's not in fact the case. For instance, let's say we take those Maxwell-like field equations that we developed earlier, the ones that look just like Maxwell's equations for electromagnetism, and let's say we play the usual game that is done in undergrad physics to show that they lead to wave equations when you combine them. This is where you arrive. And so you're like, oh, look at that. I got wave equations, and those are my sources on the right. Well, interestingly, though, if you go back to your harmonic condition, you can show that you have this relationship here between the scalar potential and that S vector. And if you also use your conservation of stress linearized, as you see there, the partial derivative, the forward divergence of your stress tensor, you can show that those two so-called wave equations reduce to effectively Laplacian equations, which means it was a mirage that gave the impression they are waves. They aren't, there's no radiative degrees of freedom in the gravitoelectric and gravitomagnetic vector fields. And the reason, another reason for this is because the so-called gravitoscalar potential and vector potential and this Hij, they have gauge freedom even in harmonic gauge, which maybe is what throws off some individuals when they work in electromagnetism, because normally in electromagnetism, once you fix the gauge, you're done. But interestingly, again, GR is a richer subject than ENM in a sense, because you could choose the harmonic gauge, which is like the Lorentz gauge, and still find you have some gauge freedom. It's kind of like still having the ability to choose Coulomb gauge, even when you're in Lorentz gauge. In some sense, there's some similarity there. So the point then is this, that gravitoelectric vector field and gravitomagnetic vector field and the two tensor fields that we defined all have coordinate freedom, which means you could make them all vanish by choosing Xi. Remember, Xi is just simply coordinate shifts. So it tells me that if I shift into a particular coordinate frame of reference, those fields are gone. Now, furthermore, it means that even in vacuum, see, someone might say, well, maybe that's just a problem when you're in matter, because after, if I back up here, someone might say, oh, well, you use conservation of stress in your calculation here. Okay, well, let's do this in vacuum. So if we do this in vacuum, what you'll find is that even the wave equations for the gravitoelectric vector field and gravitomagnetic vector field have coordinate freedom, meaning you can make the waves go away by choosing Xi. In fact, there's a special choice for Xi that has a name. It's called transverse traceless gauge, which is indeed the very gauge that we ordinarily write down gravitational waves in. So what happens basically is we find that the gauge that's commonly used in general relativity textbooks limits us to being in vacuum. That's a problem that I'm going to mention a little later that can be resolved with a better formulation, as I'll show. So just to kind of like put the nail in the coffin about no vector waves, keep in mind vector waves imply dipole radiation, and this would contradict conservation of momentum, because we know that the conservation law for linearized GR, you see here that first equation tells us that any time variance in the, say, energy density is going to turn into a flux of momentum density. And then over here we have any time variation in momentum density would turn into a flux of stress. So you would never radiate out because of a time varying momentum density. You can only radiate out because of a time varying stress. That's the one channel here, you might say, that radiates out. So it tells us you have to have time varying stress, particularly quadrupole sources that can radiate, and that's going to give you tensor waves, not vector waves. And I wrote here a list of properties. I'm not going to camp on these, but I found these really interesting. I think there's literature by Feynman that walks through how all the different characteristics of a tensor field are all interconnected. The fact that there's a rank 2 tensor for the source, the fact that there's conservation of essentially two fundamental laws, conservation of mass and momentum, the fact that there's a spin 2 graviton and the degrees apart between the polarization states. Pretty much everything kind of like lines up. You can connect from one to the other. And if you go over to a vector theory, namely like electromagnetism, you find that everything there lines up. So this is yet one more demonstration of the fact that tensor waves are what we need if we're going to talk about gravitational waves. Now, notice what happens here. This is the perturbation that we started with. It involved the scalar and vector potential. In the transverse traceless gauge, we find that the plus and cross polarization perturbation terms are in this center 2 by 2, assuming you have a wave going in the z direction. Notice that that's not consistent with the perturbation matrix we have above. That's again demonstration something differs drastically there. Now, in the TT gauge, which is usually abbreviated TT for transverse traceless, I mentioned earlier a problem there, which is that it only applies in vacuum, because you see here how the very top row is all 0, and therefore the T00, because remember by Green's function solution, I showed this earlier in the talk, that H00 is related to T00, and so if H00 is gone, so is T00, so you have no energy density, you have no matter there. Now, here's where I'd like to suggest a new approach to gravitoelectromagnetism that I think solves these problems. It clearly demonstrates gravitational waves are tensor. It can be applied in matter, and it brings in electric-like and magnetic-like features, just like we like to see in parallel with Maxwell's equations. So it eliminates the mirage. It shows us the true radiating degrees of freedom. And if you want, you can go down to what's called a Coulomb gauge in that context, and you'll still find that it's superior to the harmonic gauge. So start again, weak field. You got this flat space-time plus a perturbation. Now this time we're going to define our perturbation a little differently. We're going to define it in such a way that the 0,0 component, you could still think of it as like just a scalar potential phi. But the vector potential now has two pieces. A piece that's divergenceless, so notice the divergence of beta 0, and a piece over here that's sort of like our, that does have a divergence, like a longitudinal component. And the Hij also has multiple components, capital H, lambda, epsilon, and Hij TT, which is suggestive. That's the transverse traceless part. In fact, transverse because the derivative, the three derivative is 0, and traceless because, as you can see here, the trace is 0. Now, there's one catch. You got to make sure that the perturbation goes to 0 as R goes to infinity, which some might argue that seems a little artificial because we know we have like the FLRW metric that extends over all spacetime. And I get into a little bit of that in our paper as well, that you can still satisfy this approximation very well for the purposes of experiments that you do on Earth relative to the strength of gravity out at the boundary where all you would have is like the FLRW metric. Now, I'd like to give credit to Flanagan and Hughes, who wrote down this metric, and they actually learned it from Birchinger, who I'll mention here as well. Birchinger shows on a more general level that you can decompose a tensor into what's called a longitudinal, a solenoidal, and a transverse piece. So if you connect that to what we're doing here, lambda is satisfying the longitudinal, epsilon is satisfying the solenoidal, and Hij TT is satisfying the transverse. So these are the properties. Capital H is the spatial trace of your whole spatial part of the perturbation. And then you've got, as mentioned here, your longitudinal traceless, longitudinal transverse, transverse traceless. And your head could spin with all the different names and categorizations. But this is like the full exposition of what's called the Helmholtz decomposition approach. Now, let's go back to the transformation of the metric perturbation. And now let's introduce a gauge 4-vector C that is also sort of decomposed in a Helmholtz-like way. And I won't camp out on the details too much. I'll just simply say this. If you use that gauge 4-vector and you use the metric perturbation that we defined on the previous slide, you can show that these 4 quantities, capital theta, capital phi, capital C, and Hij tau tau or TT, are all gauge invariant, meaning that they don't change when you change your coordinates within linearized GR. Now that's pretty nice, and I'll show you why that's nice. So consider, for instance, the equation of motion, geodesic equation of motion. Write it out in terms of these new potentials. Notice you got like this gradient term minus a time derivative term. That looks awfully like a gravitoelectric field. And then you've got this V cross del cross potential. That looks a lot like a gravitomagnetic force. And then, of course, you got other terms in there, right? So, in fact, I'd also like to mention that that chi that I have at the very end is defined in terms of lambda and epsilon. I'll talk more about that a little later. But this is the idea. Define these new gravitoelectromagnetic vector fields. They're new. They're in terms of the gauge invariant potentials. So these gravitoelectric and magnetic fields, E and B here, don't change with coordinate transformations. You cannot make them disappear by changing your coordinates, is the idea. And then you do pick up a couple more fields. This last one is the L field, which turns out to be the time derivative of the theta potential. And I named it L in honor of my colleague Lance. And it was kind of funny because I did that because he named this field over here N in honor of me, Nathan. So I was just returning the favor, I guess. We needed 2 more fields, so it worked out. And so that one turns out to be negative the gradient of theta. Now, when you now bring in those tensor electric-like and magnetic-like tensor fields again, we're going to still use them, but this time only in terms of the transverse traceless parts of the perturbation, but they're defined just the same. And now look at how the equation of motion cleans up. It looks very Lorentz-like here. Got an electric field, got a V-cross magnetic field. Now, of course, you got non-Lorentz terms. You got like this velocity-dependent one over here, and this other one involving the dot product at the end field. And so they become second order there in that line. And there is a first order in velocity term right there, but then the rest are second order and et cetera. So the point, though, is that we've cleaned up the Lorentz force, gravitational Lorentz force. And now what we also find is that, I'll skip this discussion here. What we also find is that the field equations take on this form. Now, that looks hard to interpret, perhaps. I mean, you have a Laplacian equation. You got one over here that looks like it wants to become ampere because it's got the T0I. And then you got this big nasty one that's a big tensor one. Okay. Don't stare at that too long. We're going to clean up the mess. If you write things out in terms of the new gravitoelectric and gravitomagnetic fields, notice you got a Gauss law here, del dot E is equal to a source, but you do have this like displacement current in terms of the L field. Over here, it seems like you got another Gauss law. So interestingly, you have two Gauss laws, but what you can show is that in the Newtonian limit, they actually become identical because you can see they both involve T00, right? Now you have this Ampere law, which has a displacement current, but interestingly, the displacement current's not in terms of the gravitoelectric field. It's in terms of the end field. And that's an interesting indication that the gauge symmetry of GR is different from the gauge symmetry of electromagnetism. I won't go into further detail, but that can be shown to be the case. Now you still have the nasty tensor equation at the bottom. Okay, so you're still like, okay, that still looks nasty. All right, bear with me. We'll clean it up some more. Now here are the source-free equations. Like you still have the divergence-free magnetic field. The notice you have a curl-free end field. You got a Faraday-like relationship here between the E and B. You have another Faraday-like relationship between the tensor E and B. And then you have this other relationship, I don't know what to call it. A gradient is related to a time derivative of the end field. Now, let's clean up the mess some more. Here's how you clean it up. Again, thanks to Flanagan and Hughes, they showed that you can play the same game with the stress tensor. So you're going to do this decomposition business again for the stress tensor that we just did for the metric perturbation, right? Now, when you do that, you find that your field equations clean up to just 4. This is getting better, I would suggest. You've got, again, 2 Gauss laws. You've got an Ampere law that looks even simple, super simple now. It's just a curl is related to a single source. It's an abstract source. What is this R? You know, if I back up and I show you, the R is in here. It's in the T0I. Okay, these are abstract quantities just meant to decompose the stress tensor into a Helmholtz-like decomposition. But bear with me. I'll give physical meaning to them here in a moment. But the beauty here is you got 4 source field equations. Now let's bring in the ideal fluid stress tensor because we have some physical sense of what that thing is, right? It's got mass density and pressure and velocities. So what I did is I related, so this is something where I went beyond Flanagan and Hughes. I related the stress tensor components, the T00, T0I, and Tij, ideal fluid stress tensor components to the Helmholtz decomposition stress tensor. And I found that I arrived at these relationships here. So take those relationships now and now re-express your field equations. And now I would like to suggest, will the real gravito-electromagnetic field equations please stand? I suggest to you they are these. That these are what give us what we want in the sense that they're coordinate invariant or gauge invariant, if you will. They describe gravitational waves in that tensor equation at the bottom, the Ampere-looking one, but it's a tensor equation. And you've got a gravitoelectric and gravitomagnetic field, which we're all used to from electromagnetism, and we picked up this weird N field. The L field turned out to no longer, it canceled out. Sorry, Lance. But the N field stuck around. Well, I didn't choose for that to happen. That was just how it went. All right. Now, and then you have your source-free equation. So N is still curl-free. You got a Faraday relationship between E and B. The B field's still divergence-free, and you've got that Faraday relationship between the tensor E and B. So I would suggest this is the cleanest form, and I'm very, very fond of it because we can use it in a variety of ways. So with the time I have remaining, I'd like to offer some explanation of how we could use it. I'm going to skip these slides for the sake of time because I want to get to the application of these equations and show you the power that they have. There's a few other ideas here. I wrote down the Riemann tensor components in terms of the gauge invariant potentials, and then I turned around and went forward further and put them in terms of the gauge invariant vector fields and tensor fields and such. And I did find there was some interesting, what you might call inductive relationships. You see, I do want to mention there was an interesting thing. I noticed that there's a Bianchi-like relationship, like what you see here for the Riemann tensor, that exists for the electromagnetic strength tensor. And for those familiar with the covariant notation of electromagnetism, you know that that's where Faraday's law falls out of. So I thought, oh, are there like Faraday-like relationships that exist here between the components of the Riemann tensor? And I found that there was. So they're kind of complicated looking, but I think it means now, Dr. Jose Rodal and myself debated a lot on this. So I leave it still open for debate. But controversially, this equation evidently seems to indicate that near fields, this electric vector and this n vector and this b vector, which are all near fields, could induce gravitational wave fields that you see on the right. But there are reasons, technical reasons that, like I said, Dr. Rodal disputes this, and I'd love to, of course, chat and research further into this. But there's two inductive relationships, as I call them, that come out of that. But anyways, let's go to the far field where we're talking about just gravitational waves. So phi, theta, and capital C are all near fields. HIJTT is the only field that's a far field that gives us gravitational waves. So in a far field approximation, that's all we would keep in the metric perturbation. Now, mind you, it's not a gauge choice, it's a far field choice, and there is a distinction. So you can reduce your equations down to just your Ampere and Faraday-like relationships, and those Bianchi identities I mentioned reduced down too. And by the way, the reason why I thought this was instructive is because there is a paper by Thorne and colleagues that arrive at similar relationships like this with what they call Tendex and vortex fields. So I felt that's a nice connection with what they're doing. Now, I was so inspired, I was like, man, let's write a whole book on gravito-electromagnetism. So there's Griffiths and Jackson rewritten in terms of gravito-electrodynamics. Maybe one day, that would be fun. And so I'll skip past all this whole library of ideas that I have for doing that. I was given a paper to review, and I was so happy when this paper came to me, and I saw this, and red flags went up because they were calling these gravitational waves, and I suggested that they should be these, and sure enough, the change was made in the paper. I figured that's a small victory I was happy about. Okay, so I want to finish with this. You can take this gravito-electromagnetic framework, and what you can do is then write down constituent equations for different materials, like normal conductors, superconductors, or a superconductor in the presence of electromagnetic waves. So this is what I hope to maybe talk about more in a future talk, but I'll give you like a quick sample. Like if you look at a superconductor, we have like a London equation that describes the interaction of electromagnetic fields with the superconductor, giving us the London equations, and it leads to a Yukawa-like equation predicting that the magnetic field is expelled in a Meissner effect. So you can write down a similar constituent equation. We actually rigorously derive this, and you get similar London-like equations, and you get a similar Yukawa-like equation where the gravitomagnetic field is expelled from the superconductors, but it's the tensor field. So it's very nice in that sense. You can go on and use this to get a dispersion relation in the superconductor, a gravitational plasma frequency, a gravitational index of refraction, not to be confused with what that usually means. It was brought to my attention lately that people use that verbiage to refer to the way gravity causes light to bend. That's not what I'm talking about here. I'm talking about gravitational waves bending as a result of being present in a medium. And so then you can get like a penetration depth, and you can arrive at the DC limit, which is essentially like a gravitational London penetration depth, essentially. So there's like a little model here real quick that kind of shows us like when I was modeling this in a simulation, this red side is where the gravitational wave is incident. And if you look over here on like the blue side, you see how the arrows get shorter, like if you get in kind of close here. See how the arrows get shorter because what's happening is as the gravitational wave enters in, and this would be like the quadrupolar type tidal field that a gravitational wave would cause in a slab, like a superconducting slab. You can see how it attenuates, its amplitude attenuates as it passes deeper and deeper into the superconductor as a result of this formulation that I'm suggesting there in what I just showed us from the slides. So I think that's probably a good spot to kind of, if I can make my way back, oh, here we go. Yeah, it's probably a good spot to stop there. So I would like make a couple acknowledgments. So in conclusion, I'd like to first say I showed new classical forces are yet to be explored via electromagnetic and gravitational coupling and flux rules. And I showed a new coordinate invariant formulation of linearized GR, which provides a new way of describing reflection of gravitational waves from superconductors. So I actually showed expulsion, like a Meissner-like effect, not reflection. So if you want to see reflection, you'll have to invite me back one day. And a bunch of other ideas I'd love to share. So as far as acknowledgements, I'd like to thank Professor Raymond Chow, Dr. Lance Williams, and Texas Space LLC team for all of the helpful discussions and collaborations, as well as Tim Ventura and the APEC community for the opportunity to present and discuss this research. Thank you.
Well, Nathan, thank you. Thank you so much. Oops, sorry. Okay. There we go. Took my coat off. I didn't put it back on right. Okay. Let me bring everybody in. That was incredibly intense. Thank you so much. So, guys, the very first thing, we got to give Dr. Nathan Innan a giant applause. And that was like a marathon, man. Yeah, I mean, you ran so much stuff.
I just run the whole way, right?
That was awesome. And then like David and Dan, because they're both on the physics side, they were like, this is awesome in chat. And I'm just like, he lost me, but that's cool. So well, yeah, so we got like about 8 minutes for questions. Do you guys have any? Who has questions? Oh, David, go for it, sir.
Hey, thanks for your talk. Yeah, I thought it was a very good idea to take serious the tensor calculus, but still look into the comparisons of essentially heaviside gravity versus linearized GR. So thanks. Yeah, I'll have to look more into work. I was curious if you have looked into electromagnetic Hertz potentials, specifically because there's also work in the gravitational sector stemming from Sachs and Bergman from about 1958. I mention this because you had in your decomposition, your Helmholtz decomposition, your Hij term included a second derivative of some prepotential. Is that correct?
Let me grab the slide that you might be referring to. So when you're talking about the Helmholtz decomposition of the metric perturbation, are you starting at that level, or are you
there was something in your mathematics. It looked like you had an Hij that was a second derivative of some other prepotential. And I figured out just
So you're thinking of the lambda, for instance, as a prepotential because it's got a second spatial derivative of it there.
Yeah, and so I was curious if you had considered the work of Sachs and Bergman from 1958, which I shared a link in the private chat because they have the covariant formulation of getting a prepotential of the gravitational metric, which appears to be very similar to your idea, except you're focusing more in the 3-vector breakdown to kind of connect to a more electromagnetic view of things.
Right. Is that SAX?
SACHS, structure of particles in linearized gravitational theory, Phys Rev 112, 674, 1958. That one might be. There's another paper by this guy Stewart who talks about these things in 1976. Anyways, I don't want to take up all the time. Thanks for the talk.
Thank you for that.
Yeah, no, that's awesome. That's awesome. And who else? Let me see. Who else has questions? Yeah, Phil, go for it, sir.
Hey, Dr. Nader, very interesting kind of presentation. Thanks a lot for that.
Thank you.
I have a full theory as well, similar to yours, but not as complex. But I have a very simple question. Do you think the gravitomagnetic permeability is absolute? Is there any relative permeability like the electromagnetic counterpart and things like that? So yeah, that's all I would like to have your perspective on.
That's a great question. So yeah, definitely there are possibilities for the gravitomagnetic permeability to differ from that of vacuum. And that's actually a topic that I could say a couple things on. One is we wrote a paper specifically developing that quantity for the case of a superconductor. We worked on for a normal conductor. Believe it or not, just recently I came to realize dark energy can even be modeled as having a type of gravitational magnetic permeability associated with it. But probably the most interesting one is most recently we've been working on what happens if you introduce the appropriate strength and frequency of electromagnetic wave on a superconductor, induce the appropriate supercurrent, and as a result, that essentially acts as a mechanism for reflecting a gravitational wave back out. And that's something I'd love to talk about like in a future talk. And so at that stage, it gets to a point of where it's mathematical modeling to say that's a gravitational permeability, because it's not in the same sense as like atomic structure leading to a certain permeability value for electromagnetism. This is like a variety of mechanisms. Take whatever you want and call it an effective permeability that produces the result you want. Does that make sense?
Yeah, exactly. Like I'm sure the energy density would play a role in the.
Yes.
Yeah. So yeah, thanks for a very, very good answer. Thanks.
For sure.
Wonderful. And thank you, Phil. Let me see. So we have just about 3 minutes left. Does anybody else have any questions? Oh, Dan, go for it, sir.
All right, this one might be a little naive, and sorry if I comes off bad. It seems like you're making like a linearized wave equation for GR, and something very similar to Maxwell's equations. And naturally, it seems like a next step from just Maxwell's equations would be to quantize it to get something like QED. So have you looked at trying to do this with your Gravito equations? Or?
Oh, that's a tall order right there, Dan. So I mean, I have to admit, I actually almost included a slide showing that when I work on research, I tend to do everything that deals with gravity and quantum except quantizing gravity, because I've seen that the most brilliant minds have sort of like died on that hill literally, and I don't want to be another body that like dead on that hill. But I mean, I could say this, that
have you heard of entropic gravity?
What was that?
Have you heard of entropic gravity?
I have, I believe I have. It's kind of like an emergent gravity. I can't think of the name of the person. Yeah. I was just going to simply say this, though. We know that you can take Maxwell's equations and quantize them. But my understanding is that when you attempt to do that with the gravity equations, you run into so many problems, conceptual and mathematical. And I think you would still run into them, even if you're using a Maxwellian-like form of your gravitational because at the end of the day, you got to remember, even though we're calling these fields, they still represent curved space-time. We're not deviating from that, and that's at the heart of the problem.
Okay.
Awesome. Well, thank you. So, guys, I think we're just about there. So let's do this again. We owe Dr. Nathan Innan a giant applause. That was heavy duty material, but that's one of the things that makes it so exciting to be able to put APEC on, is that we're able to do this range of experimental and theoretical, and we can go as deep as people want to go. And so thank you. Yeah, I would love to have you back on in the future. I'm sure I will be. I will be on your doorstep begging for more presentations. So
awesome. I would love that.
Absolutely.
Thanks, everyone.
Hey, before he goes, I have a question. If that's okay? So, Nathan, I guess you and I both went to UC Merced. When did you start there?
I did my PhD 2012 to 2018, but I taught there 6 years prior to that. I think I left by the time you came around, maybe.
Yeah. I left at 2011 when the Fukushima happened. I joined a nuclear cleanup startup.
So I worked with Professor Raymond Chow, who is very passionate about the topic of gravitational waves and developing practical technology.
Yeah. Well, he's legendary. He is legendary.
Oh yeah, he is.
Yeah, I discussed that stuff with Ray back then as well. I was working with Roland Winston instead.
Yeah,
so
I'm familiar.
But yeah, you and I should meet and talk because yeah, there's a there's a lot going on nowadays, especially things are picking up. So yeah.
Well,
Yes.
and again, you guys can use the private chat or or email. Just let me know. Yeah, I can help connect folks if if need be. So
yeah,
That'd be
I'm in
great.
Jim's
Okay,
lab
well-
right now, by the way.
I can
came to
tell.
the lab today, so
That's
yeah.
Jim Woodward's lab. Yeah.
Yes.
I visited there.
Yeah, and actually, Jim was asking Nathan. Jim was asking about you. He got his time wrong, so I think he's watching on YouTube now, and I know he'll be watching
Yeah.
Curtis. So, and then Jack Sarfati was asking as well. So, and then Jack was watching. He was watching. I think he's been watching since the beginning. So yeah, we have a bunch of folks, and again, it's
Cool.
really exciting. I mean, a lot of it is about like the science, and then for me, a big part too is just trying to help connect people, right? Because it's a small community, and you guys are it, So
Yeah, I totally agree.
okay, well, let me do this. I'm going to take everybody out except for Curtis, and then Curtis is going to do a presentation for us. And let me do this. See if I can get this all set up here. Okay, and oops, Phil's hiding down there. Okay, Curtis, welcome, sir. So you were going to give us an update on the EM aspects of quaternion formulation for GR and Mach effects. I'm not even going to try and do a description there. That's
Sure, no problem.
yeah.
Yeah, go see my previous talks. That's probably what.
And let me see there. Let me bring your presentation in. And Curtis, thank you, man. Thank you. Actually,
Sure.
that's
Well,
I
thank you
love
for
your
letting me
PowerPoint.
present.
Oh yeah, absolutely. You are always welcome. You are always welcome. I'm going to remove myself, and I'll be here if you need anything, sir.
Okay, so hold on a second. I'm gonna get on Do Not Disturb here. Watch bugging me. So today I'm gonna cover the electromagnetism that comes out of the quaternion formulation of general relativity. This is distinctly different from what Nathan just went over because, first of all, it is a reformulation. There's a reformulation of general relativity with the addition of the additional symmetries that were discovered after Einstein, and I'll discuss more about that. And I kind of titled this, okay, there are no strings on me. I've been in honor of the great almost 3 hour or so string theory presentation that was done on that Kurt did on TOE. That's if anyone hasn't seen that, you might go and spend the time, maybe not in all one sitting, but it's a good thing. So yeah, this is definitely not along the veins of string theory, but it is changing, looking at the fundamentals a bit differently, and there's good reasons why. So I'm just going to review the story so far. So the first talk I gave here back in, I believe it was October, we covered the quaternion formulation of general relativity and how it brings together gravity and E&M. And of course, we also covered inertia and how that comes in. And later we covered in the presentation I gave in January, I went in sort of a detail derivation where we covered the quaternion matter inertia field equations and the explicit source of inertia of matter. So when there's a statement made about a theory, more recent theories where they say, oh, we figured out an inertial, where inertial mass comes from. Well, there's more than one theory that has done that in the past. So far, Sachs's theory, which was developed in the 60s and 70s, is the earliest I've discovered. So I won't make that claim that this is the earliest. I mean, who knows who thought of what? There's a lot in the literature, and unless you read all of it, you really don't you don't know. So and here what we're gonna cover here is like I said in the first slide, we're going to cover symmetries of physics and why that's important to think about when you're formulating new laws or trying to predict more interactions or more complexity that we see in nature. But what we're going to focus on here is the E&M formulation and the approach Sachs took to make a quaternion formulation of E and M, which is fairly straightforward. I think in the math side, you could consider it fairly straightforward. I would have expected, you might have expected that he went and took Maxwell's equations, the original equations that were already in quaternion form, and went from there, but that's not what he did. And I think the reason why was, everybody is taught the vector formulation and the tensor formulation. So let's get going. So what I want to review first is the symmetries in physics. And this was stems from a question I've been asking myself for a long time. After I discovered Sachs's work, the question I asked myself is, why didn't Einstein do it this way? And what I came to discover or realize, and it took a lot of thinking to kind of understand it versus, okay, here it is in your face, but understanding is a bit different, right? You got to think about it, and you get a feel for it. So Einstein, when he formulated relativity, at the time, it was understood that the laws of physics were symmetric in terms of space reflection symmetry and time reflection symmetry. Okay, so that was thought to be a fundamental nature of the universe. And it wasn't until it wasn't until that was violated, it was found in an experiment, and actually, it's clear. So that's one thing we'll talk about. And then later, what do we do at that point? Okay, there's different paths we can take, and of course, this paths Mendel-Sachs took, and we're discussing here is going back to general relativity and reformulating it, taking into account the symmetries that we know nature follows. So, as I just mentioned, Einstein included space reflection symmetry, or also known as parity, which from Noether-Serrin gives us momentum conservation, and time reflection symmetry, which gives us energy conservation with Noether-Serrin. So those were thought to be things that, okay, those are things you can depend on. They're there. Of course, a system could be dissipative and break that symmetry. That's just because things are being converted. But that was before 1956, before parity violation was discovered. It was thought that, okay, that's a symmetry of nature. And the metric tensor that Einstein came up with was formulated as a symmetric tensor in order to take into account those symmetries. Now, after Einstein, he was only around to 55, I believe. So he didn't know about this experiment, okay? He wasn't around when this happened. So in 1956, parity violation is discovered. And later on, people figure out, okay, there's charge conjugation violation. All of a sudden the floodgates were open, particle physics, the weak force, people were exploring radiation and particles and what the symmetries are. And charge parity violation was also discovered, which could be said to be equivalent to a time symmetry violation, or time reflection symmetry violation. And currently CPT, charge parity and time symmetry. So if you don't have symmetry with charge parity, that's also, you could take into account and still have symmetry with charge parity and time, where as long as time symmetry is broken in the theory or in experiments that you come up with. And so currently CPT symmetry is more or less still standing. There's always the investigations to see if that's going to break as well. So now what? Okay, so now the big question is going to be, okay, we have time symmetry and parity symmetry. So space reflection and time reflection symmetries are broken. What are we going to do? So there's two choices. You can leave GR alone, say, oh, that was done. Let's move on. Work on quantum mechanics. Okay, work on, you get QFT, you get, all the stuff that we did. And then another path that could be done is reformulate general relativity, taking those symmetries into account. And those symmetries actually inform the algebraic group you're using, right? So do that and see what happens. Now, so that's the path Sachs took. Okay, so I know previously I kind of described this, but I'm going over this because I want to emphasize that there's a very solid physical reasoning as to why you would do this type of approach. Okay, this was the approach Einstein was using. He was looking at the group, what's the minimal group he could use, and knowing at the time, that time and space were reflection symmetric, he included that in general relativity. So instead of having that symmetric, what symmetric tensor formulation, what we have is a quaternion formulation. And the thing to understand about this is that you could formulate this in other ways. So for example, and I mentioned this very briefly last time, is there are Clifford algebras you could use that kind of mathematically generalized quaternions, and you could do that. So, and you can see down here, it looks almost the same as a quaternion formulation. You divide by 2 right there, you get G mu nu, right? And this is E mu could be a Clifford generator for geometric algebra. So the thing about the algebra you use is that you can generalize it, and you can keep on generalizing it to the nth degree. There has to be a reason why you do the further generalization, right? So it has to stand on good physical reasoning why you would do that, why you would break the symmetries. It could be that you might make an assumption that a symmetry is broken, that is a more complex process that we don't know the internals of. It could be something else going on. So we got to be very careful about what symmetries we include. But at least we know that this symmetry, the time and the space reflection symmetry, are broken in nature, right? The weak force breaks this. So okay, so that's the discussion there. I just wanted to go over the motivation for the quaternion formulation, and now I'm going to go ahead and jump back into kind of like the main reason for this talk. And like I said, it's kind of straightforward. Given that you've seen my previous presentations, it might be easier to follow, but I'll do my best here. And I highly recommend going and seeing the first and second one to get a full kind of view of what this theory is about. So in terms of the E&M formulation, or the Maxwell's equations, if the concepts we're going to use here, the concepts that Sachs used to formulate this, is the generalized Mach principle. Of course, that's one of the fundamental axioms of the theory. And of course, as I just discussed, the symmetry group of relativity. Okay, so you got a quaternion/spinor representation. And of course, with the generalized Mach principle, one of the things you get out of it is the fundamental of interaction, which is what replaces the idea of a quantum effects. Okay, so basically the wave nature of matter is here, and when matter interacts, when elements of these waves interact, you get one-to-one interactions, and that's where the single interactions, the quanta that we see experimentally, that's where that comes from. So we have Maxwell's equations and special relativity here shown, and if we can formulate them in curved space-time, but we'll go back and go ahead and talk about the principles applied a little bit more in depth. So the generalized Mach principle, if you think about this, if you recall, the generalized Mach principle is not just the inertial mass of matter, but all aspects of matter, meaning the charge, the magnetic spin, whatever internal structure of matter has, whatever effects it has, or properties, those what we measure there comes from its interaction with the rest of the universe in this theory, right? So this is a strict field theory, and the dimensionality of it allows for us to have, this wave nature, a single particle or single entity interacting with all the other waves, closely coupled and weakly coupled, but it's interacting with all of them, and that interaction is what gives that generalized Mach principle. So that fundamental of interaction is tightly coupled with the generalized Mach principle in this theory. The other thing is, in this theory, there are no self-interactions allowed, right? So you get a wave is not going to wave itself. It's when it interacts with other things that, you see an effect. So without the self-interactions, you're not going to get infinities, or you're not going to get the having to do a reformulation or renormalization where you get infinities in the theory and you have to cancel them out. And as we find with quantum field theory, when you get the self interactions, you gotta take them out. The other thing is, in this theory, no fields exist without the sources. So the fields aren't standalone independent. There's always a source that produces the field. So we're not going to, in the theory, we wouldn't take the homogeneous equations and solve for that and say that's something, because that's unphysical, right? Without a source, you don't have a field. Okay. So it looks like some of my slides got messed up here. But anyway, what's supposed to be on the right is the written out explicitly, the F mu nu in terms of H and E. But that's okay. So start out with the vector formulation, right? And you could reformulate that as a covariant tensor. Okay, so kind of like the special relativity formulation. And we have E as the electric field and H here representing the magnetic field. And so, it could be reformulated, like I said here, as in a covariant form. Now, and that's unfortunate. Somehow this got I don't know why it uploaded like this, but basically what you have at the top here, it's not shown for whatever reason, it's blacked out, but it's the G's are basically the H, and let me see if I can open. Give me 1 second. Let me go see if I can open on my PowerPoint real quick. So I want to make sure I tell you guys what it is. And I did upload this, and I can make sure that it's uploaded to the server later. But basically, we're taking previously we had the H and the electric field E, and so no, you guys can't see my screen, so I'll go back to this. So basically, the G's are a complex plane representation of H plus I times E. Okay, so it's a magnetic field in the real and the electric field in the complex or the imaginary part. So you can write a set of spinor equations that have both the fields and the sources, and using those spinor. Unfortunately, I mean it's even blocking out. I'm even blocking out the differential equation I have here. But basically, there's a differential equation between the fields and the sources that it's identical to the Maxwell's field equations, which you end up with. And hopefully I can some other time get this uploaded correctly, and you guys can see that. So anyway, so there's a spinor formulation that gives you basically the same as a Maxwell's equation, and what I want to cover here is what the consequences of that reformulation is. So if you take the vector formulation, you can end up with some conservation laws and invariants that you have here the E squared minus H squared. You have the charge and current, things like that. And those are actually, the spinor formulation actually gives you those same conservation laws, but it actually has quite a bit more. If you look at that bottom equation on the right, there's a lot more going on because we have removed time and space reflection symmetry. And so what those additional kind of invariants give us is they give us force density terms that are actually odd with respect to spatial and temporal reflection. So they're different depending on how that looks. And that kind of hints at the effects that we see with the weak nuclear force and strong nuclear force. So it's, some of those things pop out. And as a review, I want to kind of go back and remind where this came from. So the quaternion formulation on the left is what replaces the Einstein field equation. As before I showed the metric tensor and the consider the metric quaternion. That's the Q. And on the right is the inertial field equations of kind of like derived from the Dirac field equations for inertial matter. So if you recall the equations on the left here, the Einstein field equations, Einstein-Sachs field equations, if you take those and you take it, you conjugate them and you combine them as you end up with a 10 equations that are symmetric per the Einstein, traditional Einstein field equations. If you combine them the other way, the odd, you call it odd combination, you end up with 6 anti-symmetric equations, tensor equations that map 1-to-1 to the Maxwell field equations. Okay, so that's kind of a short review of what we had last time. So that kind of motivates this. So we covered, in the first talk, this stuff, the big picture. Last talk we covered, where inertia came from with the background pairs, and here you basically, the slide got ruined, but maybe I can get it fixed and show it later. We covered the recovering Maxwell's equation and the details of where that comes in with the quaternion formulation. Okay, so one thing I want to, this is another slide from my first talk. There's a lot of consequences to this formulation, and one of the big ones that we've been discussing is the background pairs, which means that when in this theory, when you take an electron and a positron and you look at the ground state, they combine and they're coupled together where the electromagnetic interaction is basically nulled out, and it's in a real ground state, and you end up in the theory being able to show that if you assume that there's a dense sea of these particle-antiparticle pairs, in the field you're involved in, the space, you can call it space-time you're in, you can actually recover and derive the mass of an electron, given that interaction with that background pair gas. So again, this was something that Sachs did in the 70s, and maybe before that, I think late 60s, early 70s. And the revelation I wanted to talk about that came to me, during a open mic that we had recently, somebody brought up the measurement that the radioactive elements, for some reason, when we get a solar flare, that the radioactivity kind of slightly dips. And one of the things that's interesting is that in Sachs's theory, the rate of radioactivity has to do with the density of the background pairs. Now, the revelation to me, what's really interesting about that is that such an effect where you have some massive thing near you could be sucking in the background pairs, right, and interacting with them in a way, kind of like the analogy I gave is when there's a tsunami, right, the water goes out, and that could be what we're seeing there. Now, the other thing about this is that if that is, if this theory is correct, and that background pair density is directly proportional to the radioactivity of matter, and if we're talking about technologies that can affect that background pair density, it starts to make sense why, it's a real serious concern for, people like the Department of Energy, because then you may, if let's say you're able to lower that background pair density significantly, you might be able to, for example, get higher elements of matter, right? So your nuclei you could grow nuclei and have them stable for longer, let's say, or vice versa. If you're able to raise that density in a volume, you might make things radioactive that weren't previously radioactive. So, again, this is a as I said in my first talk, this is potential. There's potential of serious consequences to a technology like this, and I just want to say that again, that if this path really is leading us to a place where we can understand what space time, or what the background, you can call it the vacuum background, or vacuum energy. I mean, people have different names when they look at it from the quantum point of view, but looking at it from the classical, this kind of approach, which some consider to be classical or deterministic, but it's very nonlinear. So I don't know how deterministic it can be, given that things are waves and quaternions and all that. There's really significant explanations here that can move us forward. So I just wanted to mention that and give a lab update. So the vacuum is still performing pretty well. We have had trouble with our null device, and I can actually show it in a little bit if I get a bigger screen. But basically, we had built it with asymmetrically. So we usually have 3 springs on either side. There was a device built with 1 spring, and the rods weren't fully through on 2 of the ears, and so we were getting some weird effects, and we weren't getting a symmetry there. So that's been fixed, and we're actually seeing what we expect, which is especially during the mechanical resonance, we're seeing some hints of stick slip still going on, but the null device is pretty much static through the electrical resonance, what I like to call electrical resonance. So that's been fixed. So that's promising, and we're still working on the asymmetric device that passes the jiggle test. Right now, we have a device that, if you try to jiggle it, it just stays still, and it's exhibiting really explicit stick slip motion, where one side is grabbing on and kind of moving, and then it's stopping really quickly, and the thing has momentum, and it goes all over the place. So that device, like I said, it has to pass the jiggle test, meaning we've got to be able to jiggle it, and then the device needs to be able to move freely. So that's a requirement for us to be able to say anything about what that motion really is. But things are still progressing. I'm hoping at the next open mic we can give a good update as to what's happening with that asymmetric device, because one of the big problems was that with the fact that we had all the supports on one plane, it could sort of do a walking motion, and it still exhibits stick slip. We are having good results though with the composite bearings. We no longer have the issue with the ball bearings that are grinding or grooving the steel and doing who knows what with the vibrations. So anyway, so that's what I wanted to cover, and I think we're all done here.
Curtis, awesome. So let me do this. Let me see. We're only half an hour in here, man. You were fast. So we could do question and answer, or Dan had a video too. I don't have that queued though, but let me take that down. Let me put everybody back in here though. First, we need to give Mr. Curtis Horn an enormous applause. Curtis, thank you. I'm sorry that you had trouble with some of the equations. Again, PowerPoint does have the occasional glitch, right? And but StreamYard is just so useful. Other than that we kind of put up with it. But
what I'll do is I'll try to print this as a PDF, and I can upload that. So
yeah, well, I guess I should ask if anybody has questions, and and if not, we're considerably ahead of time, so we could squeeze something in too. So it's up to you guys. I see Mr. Michael Boyd snuck in. He was trying to be quiet. Okay, well, yeah. I mean, if you want, Dan, you had a half an hour presentation. Do you want to try and squeeze that in?
Yeah, we can if you want. I sent you an email that should have the half an hour one in it.
Or we could, I mean, what we could do is do you want to go to Mike first and then maybe try and squeeze Dan's in after that? And that'll keep us kind of on our schedule.
Sure.
Mike, I mean, Mike's here. Do you want to present now, Mike? Oops, Mike muted. Hold on. There.
Looks like Dr. Nader had a question in the comments.
Oh, let me see. Yeah, he's asking. Oh, okay. Sorry about that,
no
Nathan.
problem.
Okay. Yeah, Nathan, go for it, sir.
A show ready to go, no problem.
Yeah, well, let me get Nathan's question in really quick, and then.
Yeah, I was just going to ask Curtis real quick. So you mentioned some experimentation going on there. Is that something that you're doing in Woodward, in Jim Woodward's lab there?
Yes.
Okay.
Yeah,
So
I've been helping him out for the last couple years now, 2.5 years.
Gotcha. So does that mean that is your theory connected to what he works on, or are they relatively independent?
No, if the theory is real, then it's directly connected.
Okay, because I am pretty familiar with the stuff Jim has worked on. I've met with him quite a bit, and I haven't heard any discussion of quaternions and the more sophisticated topics that you're talking about. It tends to be generally on the vector level.
Yeah, Jim. Okay, so here's the thing, kind of like what you're doing. You're taking the standard formulations in E&M and gravity and using that. Jim really tries to stick with what Einstein's formulation, and with a little bit of the what people worked on subsequently, but none of those took into account the reflection symmetry of space and time that we know is real. So it's not going to have that as a basis. So now, if you're asking me, does Jim's theory get explicitly recovered from Sachs's work?
Yes,
I'm working on that. That was a question someone asked me before, and it does. But I am working on that explicit formulation because as what Jim did is he's taking the 4 vector as fundamental for momentum.
Yes.
And taking the divergence of that, and then you solve and you get that transient, right?
Yes.
Now in Sachs's theory, yes. Now in Sachs's theory, the inertial mass of matter is there's an explicit reason why it's in the theory, what it is that we measure, okay? And that explicit reason why is the background pair gas density. Now, when you put in electromagnetic energy in something, you are going to be affecting that density. And so there's in Sachs's theory, there's mechanisms for what Jim is describing. But you find there, what Jim is finding is something where, okay, it's shown through taking the 4 divergences of the vector potential and then, doing some more and concluding with that. But that doesn't tell you why it's happening deep down, right? So Sachs's theory is maybe maybe it's the right direction, maybe it's the right path, right? So we're searching under where the lamps are, right? The lamps are where everybody knows what works. Sachs went on his own with his own flashlight over there, and he's looking at something else, okay? So if you're interested, we can talk more about this, but
sure.
That's the thing. I'm Sachs, he passed away, I think, in 2011. So most of his work was done in the 70s, and it's basically if you get rid of time and space reflection symmetry, you could do it yourself, and you get a quaternion. You could use a quaternion. You could use a geometric algebra. Just be careful how complex you make things, right? So if you look at what Eric Weinstein was talking about when he's asked about, okay, well, why quantize gravity? Or he's like, why not the other way around, right? This is kind of the other way around approach, where you're taking gravity, and instead of having a dual, you have a single. You could have like I said, you could have a geometric algebra, you could have a quaternion algebra. To me, they're kind of related, right? And but we're doing physics, not math. So we need to have a physical justification for the algebra we pick, right? The symmetries that we picked as fundamental. And I'm not saying SACS is the answer, but it's a different approach, and I think it bears exploring.
Thank you.
Awesome. Michael, did you have a question? Yeah, go for it.
Oh, Curtis, you were talking about the effect of solar flares on the radioactive decay rate, and what that was about was actually it wasn't the solar flare, but the coronal mass ejection. So
Okay.
the solar flare takes, if we're in line of sight, it takes 7 minutes to get to Earth, but the coronal mass ejection takes 3 days to get to Earth. Because it's kind of like a gravity wave. It's a million-mile wide wave of space and time heading towards the Earth.
Thank you for clarifying that for me. I did misspeak, and the coronal mass ejection. And I did see a study where they were looking at the Earth's rotation and seeing if when the Earth was closer to the sun, is there a difference in radioactive rates? And
it was based on when they got it. It was a day and a half before the CME occurred. So basically, what happens is you have solar flare and the CME pretty much simultaneously. The CME is a little bit behind in time, but this event, this decay rate change, occurred a day and a half before. And when we talked about it, you said, "Oh, well," you brought up the thing of a tidal wave. Like before the tidal wave comes, the water level drops,
recedes. Yes.
So I think you're right on the money. I'm just clarifying that. What was cool about it is it's like a gravitational pre-signal, and what my hypothesis is that's associated with expanded space-time, a region of where the density of space-time is lower.
Right.
Follow?
So here's my comments are this, that so we're taking in SACS theory, you're taking this density of background pair gas, and then I want to be careful about what we call space-time, because here we have a quaternion basis, so it's not really a space-time anymore. It's weirder than that. It's more abstract. So, but that's our terminology, right? We talk about space-time. So in the density, it could be that the density is decreasing, and that causes the instability in the sun, and there you go. You get this.
But then we get a gravitational lensing effect where everything's blue shifted in that region. It's blue shifted, which means that time is actually, or if you think about it, variable speed of light. Speed of light is faster. Things go faster in that area than they do closer to the matter, for example.
Yeah.
And that's
the big question for me.
In theory.
Right. Yeah. So the big question for you. So with the background pair density gas, you end up with something that has, the permeability and susceptibility that we measure in the vacuum, and that comes not just from just saying that it's E&M, and there's that thing there, that concept. This comes out of basically taking this quaternion formulation of E&M, from that, taking that you take the symmetry, the reflection symmetry of space and time, you get rid of it, you reformulate general relativity, you get a quaternion formulation, you combine it together, you end up with equivalent Maxwell's equations. You use that to see what happens when I get an electron and a positron coming together, and you end up with predicting a background pair gas. And that background pair gas density gives you what we measure as the inertial mass of an electron. So none of that comes from it. It's just assuming the symmetries and assuming covariance, right? So there's some basic things that give us all that, and that's a whole different approach than the quantum, quantum thing. It's a very different way of looking at things. And what's striking is it's giving us the same predictions.
Awesome.
Yeah. Thanks.
Thanks, Michael. And let me see. Does anybody else have questions for Curtis?
Hey, Curtis, have you ever implemented Lorentz transformations with quaternions? It's a little difficult, isn't it?
Yeah. So with Lorentz, okay, so the special relativity is really not in this theory. It's okay. It's there as like something you gotta reduce down to, like correspondence principle type thing, but you don't necessarily. I mean, the theory is pretty, I would say, onerous, right? It's a coupled field theory and closed, but every entity is interacting with every other entity, however weakly, and so there's a lot going on. So those approximations or simplifications are there. You can do them, and yeah. So that's what I would say.
Awesome. Let me see. Do you guys have any more questions? And if not, we can go to Mike, but I want to double check. Okay. Well, Curtis, let me thank you once again, sir. Guys, let's put our hands together. Wonderful presentation for Curtis. Thank you so much. So I'm going to take everybody out except for Mike. We're going to go to Mike Gamble's presentation. Let me see. Okay. And Mike, let me see. There we go. Okay. I've had my heat lamp on to keep this place warm and it's putting me to sleep. So I just popped the door open. So Mike, the work that you've been doing on the Graviflyer, you've been working with Jared and Charlie, and then you've been working with Alexei Chekurkov. And this is absolutely amazing. Jared and Charlie have been giving us regular updates, and I think they have new ones for us today. But I don't think that you've given us an update yet. So thank you for coming on to share that with us. Let me see. I think, do you want me to put this one up? Flying saucer propulsion?
Yeah. First question is, how do you work the slides on this thing?
Yeah, so if you put your mouse over it, there should be a back and forward button, and then there's also a little drop down where you could select the actual slide that you want to use.
Well, okay, I don't see any arrows.
It should be down there at the bottom. Towards the bottom of it, there should be a little bar that says slides back and forth.
I don't see anything like that.
If you move your mouse over the flying saucer propulsion. And you can use your back and forward key too.
Okay. It's a hidden one.
Yeah.
Gotcha. Okay.
Okay. Well, and I will be here if you need me. And at some point, I see you've got a video loaded too. I can bring that up, and so I am here, sir. Just let me know when you need me.
Way in the back there, I run the video, but we do a little bit of theory and a few number crunchings and stuff like that.
Okay. Yeah, well, thank you for presenting this. Thank you for sharing us, so the mini sermon on flying saucer propulsion.
Yeah. Well, a little history on this for starters there. Originally, this was presented at Tesla Tech back in August. Since then, we've worked on it another 6 or so, and so there's a revision on it, updated and all that. For those of you that don't know me, I'm Mike Gamble, retired electrical engineer for Boeing. I put in 30 years, ran an R&D lab and building all kinds of fun stuff. However, this is not my normal Tesla resonant motor work, which I've been doing for quite a few years. A little bit of a mini sermon in reverse engineering. After last year's Tesla Tech 2022, a few of these guys you just mentioned twisted my arm to do research on the Graviflyer here. And this is my findings that I found on it. And okay, so we are working. If you're going to do a sermon, you start with some text. So the first text there, it says things which you are seen are made by things which are unseen. That one's out of the Bible. Second one is high technology is indistinguishable from magic. That one's from Clark. And so we'll start by mentioning some unseen things like temperature, pressure, electricity, to name a few. You cannot directly see any of these things by themselves, but only the results or actions of them. And I'm sure you can think of plenty more. Oh, okay, you don't have to click on the thing. It goes by itself. Learning. Another one, wind is a good example. Unseen things. Standard meteorological weather map there shows winds. And the winds blow where they will, and you hear their sound, but you cannot tell where they come from or where they go. That's another one out of the Bible. Digging deeper, weathermen will tell you that wind is the movement of air from high pressure to low pressure area. However, it's still a poor or incomplete definition. This one, going down to the next level, if winds are unseen, then the forces generating them are even more unseen. We have a high pressure area here showing air leaving an area in the blue. And we have a red over there, low pressure area, where the air is entering the area. The part that isn't saying or said is that those pressure areas or differences are caused by force fields. Going down to the next level, there's two ways to generate forces. You either do it mechanically or electrically. First one there, you could just give it a swift kick. And the second one is the left-hand rule. This is electromagnetic, shows that a force can be generated by unseen electromagnetic fields. If the happy face represents an air molecule in the field of this planet, it's going to move, and we call that wind. Tesla measured the frequency of electrical thunderstorms way back when, back in Colorado there, which is a lot of wind blowing, to be about 125 kilohertz. And this one, if you think the wind example was just a lot of hot air, you can try this. You stick your finger in an electrical outlet, you'll definitely feel something. Electricity is odorless, tasteless, colorless, and weightless. However, from a safety standpoint, I wouldn't recommend it. Now that we're down to the high technology, a magical, mystical subject of unseen electromagnetic fields, we'll start the detailed analysis of the Alexei Graviflyer. Seeing how this subject involves Earth's gravity, the following is a very simple definition. Acceleration of gravity is 32 feet per second in English, 9.8 meters per second in metric. However, a little lesser known fact is it also equals a force of 9.8 newtons per kilogram, because force equals mass times acceleration. For the basic theory, we're only going to analyze a very small section of the Earth's gravitational field, something that can be assumed to be essentially flat rather than round. Then we'll put something into the Earth's gravitational field that generates an independent radial force field and see what happens. Quick test of the 4 points at the top, sides, and bottom shows that there's no possibility of generating lift. At the top, point A, the fields subtract, nil, or cancel, which is going in the right direction. The sides, points B and C, don't do anything because the fields are perpendicular to each other. However, at bottom, the point D, they add, so what you gained at the top is now lost at the bottom, and net lift is 0. Moving a little bit more on the analysis, test case there, it shows that if you change the lower portion of the external field, reverse it, also known as polarization, I put that in big blue arrows there, there's now a possibility of generating lift. The side points, B and C, still do nothing because they're perpendicular. However, now both the top and bottom points, A and D, the field subtracts, nil, and cancel, which is definitely working in the right direction. So there's a possibility of making some lift. The conclusion of this test is that a polarized local force field is needed to generate lift. Two ways to that is one, you can generate two nodes of an opposite polarity, i.e. a dipole shown on the left, or two, generate a single node of polarized field shown on the right. In either case, the main lobe field strength, the red and blue arrows, is going to have to be greater than the Earth's field of 9.8 newtons per kilogram. The side lobes, highlighted in yellow, they're basically irrelevant for lift. This is a picture of the Graviflyer running in Alexei's home. It's the exact unit that I presently have sitting on my workbench for study analysis. It gives me good confidence that I'm not wasting my time playing with a non-working unit. This is a close-up view of it sitting on my workbench. However, had to make a few repairs to it. There were some worn parts and it had some transportation damage getting to me, but it's fixed up now. Show you what the main parts are. Up on top, you have a 1-inch diameter piezo ultrasound generator sitting under a feed horn that focuses the ultrasound in the down direction. It runs 20 to 60 kilohertz, somewhere around there. Right below that is a 8-inch diameter aluminum plate that spins in the clockwise direction. It's charged to 10 kilovolts DC. Below that is the center plate. It's 15 inches in diameter. It's also stationary. It's bolted to the 3 rods there. And it's charged to 2 kilovolts AC from a Tesla coil. Below that, you have another 8-inch diameter disc, which spins counterclockwise, and it's charged to a negative 10 kilovolts. This one also has 6 permanent magnets around its perimeter, 1-inch diameter Alnico magnets. These 2 rotors are spun by 2.5-inch DC 12-volt fan motors. And the frame, whole thing weighs 1.36 kilograms or 3 pounds. Going over to the theoretical side a little bit, we take a look at a basic disk, and then we put a high voltage charge on it, and you get a uniform field all around it. If you put a positive charge on it, you get the arrows pointing out. You put a negative charge, you get the arrows pointing in. And in both cases, the higher the charging voltage, the further the field spreads out. This one chart here shows a positive 2.7 kilovolt charge on the plate. And there's a cal point over here, 20 millimeters, so we don't burn out the calibration probe, because we have high voltage on there, so you want to stay back behind the arcing distance. And when we plot it, we get a little bit of nonlinearity, because I think it's the spin that causes it to do that. And the measured cal point with the 2.7 generates a field of 45.08 kilovolts per meter field strength. And then plotting this a different way, this is a cutaway view of the top and bottom plots there, the 2.7 kV DC field. And I only highlighted the perimeter of the disc so that the bottom here doesn't get, you can see it, and the cal point's over here. And your red is your high voltage and the blue is 0, or background, whatever you want to call it. Going to the bottom disk, that is charged by a negative 5.2 kilovolts. And this one I had problems with MATLAB. All these graphs are MATLAB generated, and it would not integrate negative numbers. Didn't like them at all. So what I did is I integrated the 5.2 as positive and then threw a negative sign on it, so the arrows are backwards. And this generates a field strength of minus 86 0.82 kilovolt per meter. And then we go to the field plot of it here. Again, the blue and the red should be reversed because it's negative voltage. And it's just the perimeter of the dish showing along with the cal point. So the 5.2 generates the same voltage, and then the cal point voltage off to the side there. Okay, and we go back to the theoretical there. Now, if you take this charged disk and you spin it, in addition to the electric field, you now get a magnetic field, which is highlighted in red. And it's a function of the charge voltage and also of the RPMs. So the B field now has two calculations in there that you have to deal with. So then we do a field plot on that. And so this is the measured field plot of the top disk with 2.7 kV on it, spinning at 1700 RPMs. And the cal point had to be moved back 50 millimeters for the arcing problem. And when you combine that speed and that voltage, you get a field strength of 46.02 microwebers per meter squared. And you also notice that there's a dip in the center of the field, which is shown from the theoretical at the center of rotation. To highlight that, I changed over to the R and Z axis rather than the other one because it highlights the dip. This is basically turned on its side. Usually the R is this way and the Z axis is up and down, but the picture looks better laying on its back. And then we do a similar thing for the bottom disk, which is charged to 5.2 kV. And it's only turning at 1160 RPM. And it generates 60.47 microwebers. And this one, because the RPM is lower, but the voltage is higher, so the field strength still comes up a little bit more than on the other one. And same problem with the color. MATLAB didn't like negative numbers, so had to cheat a little bit on those. And similarly, you go switch over to the R and Z axis. It highlights the dimple in the center there of the field. However, the colors are also reversed on that one. And then we go down. The previous two charts didn't show the permanent magnets on there. So this one shows the field strength of the magnetic field generated by the spin of the disk. The top one shows the 6 permanent magnets. Their field strength is about 70 microwebers, along with the 5.2 kilovolts spinning at 1100. So now we go back to the theoretical there, combining the electric field and the magnetic field. You get a force field that's generated in blue. And okay, this one is the top one, so it's spinning clockwise. So the asterisk is out of the page, X is into the page. The electric field is pointing away from the disk. And the cross product gives you the blue force vector. As you can see, it rotates from the center out. And what that generates, this is a 2D side view of a 3D rolling, spinning, twisting, three-dimensional torad shaped force field. And then the next one, we change it to the bottom disk. Now the E field changed direction, and the disk rotation changes direction. This is now counterclockwise. However, the vector cross product does not change, so it still has the same rolling twisting that you got from the first one, in spite of the fact that you now have reversed voltage and reversed rotation. You still get the donut-shaped torad. These are a little, shows a little more detail of the three-dimensional. On the top plate, the spin vector is out on the perimeter and clockwise. When you translate that to a 3D picture, that's what the shape looks like. Same thing for the bottom, only it spins the opposite direction, and you can see the spiral is going the other way. Now, these two force fields are isolated by the center 15-inch diameter disc. We started this analysis with a very simple definition of gravity, but for want of a better gravity's definition, previously I'd done 2 presentations for Boeing for them back in 2009 and 2010, which dug a little bit more into it. Those are, I think I presented those here earlier, but the conclusion of those studies was that gravity was defined by a B field and an E field. The B field basically has a DC term and 2 AC terms, a fundamental and a second harmonic. Now, the DC term is what your Boy Scout compasses lock onto. The E field only has 1 term, which is the second harmonic. And when you do the vector cross product, you get 4 terms of force. You get a fundamental, you get a second harmonic, third harmonic, and fourth harmonic. And this is a real rough picture just to show the workings. The B field is your standard torad. The part DC is what your compasses lock onto, but there's also a first and second harmonic where they swirl back and forth. At the same time, you have the E field, which is spinning back and forth. This particular one shows it's in counterclockwise position, and the B field is down, but the next half cycle, it'll turn the other way. However, the resultant force field, it stays radial. This chart shows the gravity harmonics, the first 4 harmonics. These are the same numbers Tesla measured way back when. The fundamental is 7.07 hertz. Second harmonic's 14.14 hertz. 21.21 is the third harmonic, and 28.28 is this fourth harmonic. These drive the resonant cavity of the Earth, which generates your Schumann frequencies over here on the left. And if you look at the motor harmonics, or the RPMs, the motor RPMs covers the entire range from the fundamental up to the fourth harmonic. That's one of the things that I discovered when I started doing the analysis here, is the thing is completely covered with gravity harmonics. Okay, this chart does the sound resonance for the 8-inch diameter disc. And it does, I do the calculations for the thickness, for the radius, the diameter, and the circumference. And when you run the numbers, the fundamental on the thickness, this is the ultrasound going through the thickness, you get 4 megahertz, 8 megahertz, 12 megahertz, 16. On the radius, you're down in the kilohertz range, 63, 126, up to 256. Diameter is essentially half of that. And when you get out to the circumference, it goes even slower. You're down between 10 and 40. The second harmonic here at 20 kilohertz. On the next chart, we flip over to it so I figure out how to push the button. There's also an air gap between the top disc and the center plate, 25 millimeters, which is a half wave resonant cavity. And if you run its numbers, The fundamental is 6.86 kilohertz. The second is 13.72. And the third harmonic is 50.58 or 20.58, which is close enough to resonate from the plate vibration, which you see up here. Oops, I just screwed up. Hang on a minute. Let's try that again. Wrong button. So the third harmonic of the air cavity resonates with the second harmonic of the plate resonance. Now, if you increase this air gap just a little bit to 25.6, then it will dial right into the 20.144 from the previous chart right there. So that you can bring those in by just adjusting the air gap. Okay, now we move on and do this. Pretty much the same calculations, only now we do it for the electric field rather than the sound field. And when we run those numbers through the thickness, this is down in the kilohertz range, 100 to 1600. The radius is now down into the low hertz, 25. The diameter is down 6 to 102, and the circumference goes even lower to a fraction of a hertz up to 10. Now, the ones highlighted in red are going to resonate with gravity, which is down here 7 to 28, and the thickness is going to resonate with the high voltage 1.2 megahertz in that range. Now, the next chart, we take and compare the sound resonance with the electrical resonance, and we see a real strange happening up here. The sound goes through the thickness of the disc, it gets kicked up to megahertz, and when the megahertz electrical signal comes through, it gets kicked down to the kilohertz range. So the beat frequencies between these two are going to find a happy medium somewhere on a resonant harmonic, which appears to be odd. And looking down here, you're going to be operating down in the gravity range, so you're going to be resonating with gravity. Now, taking a look at the discs on vibration, okay, this shows the even harmonics, second harmonic, fourth harmonic, sixth, 10th, and 12th. If you take the 10th harmonic, which has a wavelength around the edge of 25 or 2.513 inches, and then it has 3 cycles on the disc diameter, that comes up to be 2.667 on the diameter. So they're not the same, so they're unstable, so because there's going to be interference patterns that are going to be destructive interference, so even harmonics will not sit on that plate. Now, switching over to doing research on the odd harmonics, 1, 3, 5, 7, 9, 11, taking the 11th one along the circumference, that's going to come out to be 2.285. And if you look across the diameter, you're going to see 3.5 cycles of the wave. Running that number comes out to be 2.286. So there's not, this is constructive interference rather than destructive. So you will have odd harmonics on the plate. And if you look at the wave ratios here from the harmonics, all these are kind of odd numbers, except for this one on the 11th harmonic. It goes 11 on the circumference and 3.5 on the diameter, where the other ones have some odd harmonics in between there. I would say, well, excuse me, 11 is going to be the most stable one. Okay, now we do very similar procedure, only on the large disk. Looks like that thing got moved over a little bit, and the charts got smudged, I guess, or crunched. Anyway, same thing, only this is a 15-inch diameter circumference. We do the thickness, the radius, diameter, and circumference. And going through the thickness now, the megahertz changes a little bit on the sound. Radius is down in the kilohertz. Diameter is down in the kilohertz. And the circumference is down in the kilohertz. Now, the blue highlighting will resonate with the ultrasound, and the green highlighting will resonate with the electrical. So then we do a similar thing. This one is the electrical side going through the thickness. This kicks it down into the kilohertz range. The radius is now kicked down to the low hertz, same as the diameter, and the circumference goes way down into the hertz range. Blue is highlighted in the ultrasound, and the red is highlighted in the gravity range. And then we do a similar comparison between the two, and same thing happens. The sound frequencies get kicked up into the electrical range, and the electrical frequencies get kicked down to the sound range. So when they're vibrating back and forth, they're going to find a happy medium at probably an odd harmonic when they're going to synchronize. And the end result is you have more gravity numbers being resonated down in the very low end. And then basically what's happening is you're shifting from the megahertz down to the kilohertz, down to the hertz range. And the ultrasound is the one that's doing the level shifting or the heterodyning between the electrical to get down to the gravity numbers. And this one shows the principle on how the center plate is working. To operate that 15-inch diameter disc as a reflector or a mirror, you have to polarize its surfaces. And this shows being done by different frequencies. Then we'll switch over to expanded view where we widen the plate distance out so we can see what's going through the distance or through the thickness of the plate. What's happening is the waves are coming in through air, and then the media translates to aluminum, and then they go back out to air. So the wavelength changes tremendously as you go through the plate. And the end result is, if you go to the fundamental, there's a half a wave it takes to go through the plate, which is 14 kilohertz. And then this would be the third harmonic, but it comes up squared. So this is the first squared, third squared, fifth squared. So it goes 9, 25th, and then 7th would be 49th. So this one is a half a wavelength, does the shifting at 14 kilohertz. This one is 1.5 waves to do the shifting at 126 kilohertz. And this one is 2.5 wavelengths at 352 kilohertz to do the wave shifting to polarize that plate. And now if things are working right, I'm going to have him come up and tell me how to bring up the, I got to get out of the, to bring up the chart.
Yeah.
And see what happens here.
Yeah. So Mike, let me do this. I'm gonna remove that, and I'm gonna add that to stage. And I think, yeah, there we go. It's already auto playing.
Yeah, it's running right now. Yeah. I'm just gonna shut up and watch it, and then I'll tell you. I'll have you run it the second time.
Пошла. Есть. Сейчас. Зафиксируем, попробуем стабилизировать положение, чтобы не шаталось. Сейчас, минутку. Вот это кольцо сейчас пропустим через этот вверх. Как видите, тут нет разрывов, ничего. Сейчас я накину все. Ну вот. Есть, летит. Так. Убираем клемму. Нужно постоянно регулировать. Вот она все висит. Она даже смотрится как НЛО. Домашняя гравицапа. Сейчас убираю клемму с катчера, и она сейчас долбанется. Не так быстро, правда, медленно. Все убрал. Сейчас ждем минутку.
The video died.
No, I think it just ended. Yeah, look, yep, it's all done.
Well, it's supposed to crash to the floor. Anyway, if you can rewind it, and then I'll talk over it and tell you what's going on. Okay, the scraping sound you hear is the high voltage pickup feeding the high voltage field, and then you'll start
Начинается. Сейчас поймаем момент отрыва.
because the discs are out of balance. Right there is where the torque field is.
Пошла.
Okay, there's two fields that you can't see that are lifting this thing. And as the fields increase, it goes higher.
Стабилизировать положение, чтобы не шататься.
So there's two torsion fields that's lifting this thing, those two torads, one above the plate and one below the plate. And then he walks over there and throws a hoop around it to show you that there's no lift wires involved, that it's purely electromagnetic.
Видите, тут нет разрывов, ничего.
And then he comes back and he starts reducing the field strength, and it starts going back down. And video died before it hit the floor. So, you can see it lowering now.
Нужно постоянно регулировать. Вот она все висит.
We'll see if it'll run the
Она
full
даже смотрится как НЛО. Домашняя гравицапа. Сейчас убираю клемму с катчера, и она сейчас долбанется. Не так быстро, правда.
You can see it coming down now as he lowers the field strength.
Сейчас ждем минутку.
No, the video dies first, but it gets down about 6 inches off the floor, and then it crashes when it comes out of sync. So there's, but anyway, if you can put up the pitch charts again, we'll continue on. There we go. Okay. And the conclusions of this, what it's doing, it operates by nilling or reducing the local area electromagnetic field with those two torads or toradal fields. And this in turn nils or reduces the local area force field. It's essentially a two-step process. However, it doesn't actually generate lift, but floats on the electromagnetic field. To put it another way, it basically creates a bubble in the ether. If I happen to go for that type of background. The ultrasound and the RF frequencies will resonate at odd harmonics in the disc thicknesses, and they must be synchronized. And this high frequency disc thickness resonance is then stepped down or heterodyne, whatever you want the fancy terms, down to the gravity frequencies, low frequency RF or AC or whatever you want to call it, through the disc resonant plate dimensions, the radius, the diameter, and the circumference. And it's also not a true anti-gravity device because it actually requires gravity work. It phase shifts it. However, the big gotcha is number 8. It has to be resonant with and synchronized to Earth's gravity to function. That's the tricky part that everybody's working on to make this thing go. Therefore, the device's operating range will be limited to the Earth's gravitational field, which is 22,000 miles out to geosync. And hopefully I've not bored you with all the numbers that engineers have. So I thank you for watching reverse engineering of Alexei's Graviflyer, and we'll take any questions you can throw at me. As soon as Tim pops this thing out of there.
Oops, sorry, I was muted. Yeah, let me pop that out of there. Before anything else, though, I'm loading up on caffeine behind the scenes, so I'm getting my second win. Yeah. Okay, so for everybody who's here, let's give Mike Gamble an enormous applause. Mike, thank you. Thank you. The Graviflyer is really exciting right now. So, and actually, we have Jared here too. But yeah, I guess I should ask who has questions. Who has questions for Mike?
I have one question, if I may.
Yeah, go for it, Nick. Go for it, Nick.
You said the resonance of Earth's gravity. Do you mean that there's a frequency associated with Earth's gravity?
Yeah, there's 4. 7 harmonics, or 7.07 hertz is the fundamental, and it goes up to 28.8 is the 4th harmonic. There's
What
a
causes?
DC term. Which?
Wait, you said it's DC? It's DC, not
No,
AC? Well, I mean,
there's a DC term on the magnetic field, and then there's 2, a fundamental and a 2nd harmonic on the B field on the magnetic side, and on the electric side there's only a 2nd harmonic.
do you know what is the physical cause of an oscillation in the field of the Earth?
Yeah, it's a big electric motor.
Well, do you mean because it's spinning?
Well, that's part of it, but that field is what generates the gravity field, or gravity waves, whatever you want to call them, that hold this place together.
Well, so Mike, if it's okay to jump in, let me ask, where are you at with, because I know that you're testing one of the devices that Alexei sent. I mean, how are you feeling about that? You know, because I would say it's controversial, you know, and the part that gets me is like, because I talk to Jared and Charlie all the time, and they are so excited, and the more I talk to Jared, he's just like, yes, this is for real. Yes, this is for
Matter
real.
of fact, he's coming over here the next week.
Yeah. So, I mean, do you feel like you might be able to get this thing to lift off?
I'm sure. Well, I have 100% proof that it works, because you just seen the video. That video is the exact same unit that's sitting on my bench, which is about 3 feet from me right here where I'm at my desk. And
Yeah.
I have no reason to believe that it will not work. Step number 8 there is you have to achieve the resonance and the synchronization. Now, the resonance comes easier than the synchronization. Gerard can probably back me up on this, because they're working with Alexei, and he goes through quite a, I'd say, call it a complicated procedure to get the synchronization on this thing. He turns a bunch of knobs, pushes some buttons and everything else, trying to get it synchronized. And if it doesn't synchronize, then he has to shut it all off and start over, because the field has to be back down to 0 before you can bring the field back up. The synchronization and resonance is where they have their problem. What I'm trying to do is to supply electrical engineering to it, putting on sensors and that, so that they can get him to run it, and then we can do a data logging of where the perimeters are when he actually gets it to pop off.
Yeah.
Because
yeah.
he just guesses in the dark, you know.
So you're adding the real science aspect of it, and it sounds like a lot of parallels with when I hear John Hutchinson describe when he was getting certain effects, and that it's getting these specific resonance and together with the fields, right?
Yeah, he could do it, but anybody tried to duplicate Hutchinson's work could never get it to go, because the secret sauce or magic chef touch, whatever you want to call it, Alexei's got it. We don't.
Well, and so yeah, for Nathan, you're not familiar with the Graviflyer, are you? Have you seen that at all?
I'm not. No, I'm actually reading up on it right now as you guys speak. I
just
didn't realize
be
this.
careful. It will stick in your head and drive you slowly insane. And then
my arm.
It's I think that we should rename it the Hold My Beer Drive, because you look at the videos and there's no way this is for real. But then it like sneaks up on you, and next thing you know, you're like, there's no way this is for real, and yet, you know, it's like you've entered the Matrix. So
Well, the presentation I just gave you was a year's worth of studying on it after they twisted my arm. I thought it was bunk too, but you start doing the science on there, and the numbers are there.
And then I've seen like Jared's spreadsheet. Oh my God! And what's that? That's like 100 by 50 columns now of data that he keeps logging on it. It's like he's nodding his head. Jared's been living on down there on the lower left hand. Jared has been living on caffeine for like the last 6 months working on this thing.
Yeah, there it is.
It's so Nathan, don't get too close to this is the one that kills scientists, you know. This is like the great white whale from Moby Dick.
Until they get it working in the next one, right? I can't wait to see it.
What you got, Curtis?
Well,
I have a question. So is there any I noticed that, you know, in the original there was a piezoelectric. Can you discuss more what that piezoelectric is doing? Maybe repeat that part.
Well, you have a whole bunch of frequencies all beating together. You start off with a megahertz range from the Tesla coil, and the ultrasound comes in there, and it generates a beat frequency, which shifts all this down to the low frequencies. They're level translating, uplink, downlink type operations using ultrasound.
And have you looked at the Mega Drive, the Jim Woodward's work?
Yeah, I was just thinking that's kind of another great white whale, isn't it, Curtis?
And the reason I bring this up is that you know, when Jared brought this, and you know, this has been something we talk about, especially on the open mics. I see a lot of parallels with because we're using a piezo stack, and there's an asymmetry there, and there's a lot of electromagnetic energy going in and out.
Well,
now the thing I've got to be the thing I got to caution you guys about is that we did a COMSOL multi-physics simulation of the piezo drive. I'm the Mach drive, the Mach effect drive, and we found that in air, because of the asymmetry that's inherent in it, we end up with a force with our little device of a Newton, just from air effects. So that's why I would caution doing that experiment in air, especially you have a piezo vibration, you have electromagnetic energy coming in. That vibration
the lift on this thing, the lift is 3 pounds. That device weighs 3 pounds, so it's not air doing the lifting.
There's something I got to jump in here, Curtis. I got to jump in because this will help. So just this last week, Charles was doing some measurements on Alexei's ultrasound circuits, and massive insight. It shows that it has extremely fast rise fall times. So sure, it's 20 to 50 kilohertz, but those rise fall times are like a microsecond. So
by the way, in that vein, we found that the Mach effect drive works better when we use a sawtooth wave. So the dPdt is like one of the first terms in Jim Woodward's equation. So
it's interesting, the overlap, because at a microsecond for a rise time, that's about a megahertz, which is about the frequency of the Tesla coil. So there is some overlap. Like Mike was saying, the ultrasound seems like it's the translator between the electromagnetic and the mechanical, because you have this electromagnetic 1 microsecond rise time Tesla coil side, but you also have the mechanical where it's banging that center disc drum and causing the whole thing to vibrate. The weirdest part, though, of the whole thing is that the whole thing lifts when he turns off the ultrasound for a brief moment, right? When he removes that pulse that is lined up with the Tesla coil, that's when the thing actually goes, okay, let me invert the fields and lift.
And you've seen the field inversion, dude. It's again, one of the interesting things is Alexei makes all these claims. And one of the things that Jared and Charlie have been talking about is as they go through and they replicate this, right, Jared, you turn off the ultrasound and you see those fields invert. The voltage goes from the top plate to the bottom plate. So they're seeing all these little associated effects, which is just intriguing. You know, it grabs
charge transfer from the bottom spinning disc up to the top spinning disc, or from both of those discs to the center disc, at the same time that you get a big EMP.
So this is the size of the device. This was giving a Newton of force. You have a lot bigger device there, and if you're having the same kind of vibration effect, vorticity, or whatever you want to call it, I would get it out of there. But all that being said, what you're describing has a lot of ties with the theory that Jim Woodward came up with, because of the dPdt, and you're putting that electromagnetic energy in and out. You have that change in acceleration happening, and so I would highly suggest getting it to work in a vacuum, and the vacuum has to be really good, like at least 10 to the minus 4 torr. Because even like a millitorr level, there's questions, right? We got a helicopter on Mars, okay? So we know you got to get out of that regime where air has vorticity, so it can push against itself, right? So that's important. But what I find striking is that there's similar themes going on with the Woodward drive. And if you look at that equation, what you guys are describing has a lot of dPdt and has the motion as well. You're doing some spinning, that's fine. That's in there too. That'll also cause that vibration.
Curtis, the thing that excites me is believe it or not, it's not like right now, right? Like when you look at this screen, you've got two folks in California, BurnEye's in Canada, Drew's in Florida, Jared's in Oregon, Dan's on the East Coast, right? I mean, we've got folks spread across the US and realistically folks spread across the world. And I think the one difference definitely when I first started getting interested in this, the one difference now is we can interact and work together in real time. And that is super exciting. The other part too is you have physicists, you have engineers, and you have garage inventors working together, and I mean, it is just like the sum of us is more than, all those constituent components. So for me, that's the really exciting thing, because we've seen like these ideas and, mathematical concepts and rumors and devices going back like 70 years now, and no one's been able to repeatedly pull it off. But I keep thinking, you know what, with this, and this isn't an APEC thing. You guys do independent Zooms, you have independent meetings. It's just the enabling technologies that are there for people to work together. That's what I think is going on. I think that's going to make it all happen. So That's sorry, my cheerleading. It's part of my
Assembling
job.
the APEC dream team, and then it's like once you get this one working definitively, or like learn from it and take the certain aspects and apply it to the other technologies and different claims and cases out there, eventually I see APEC probably going to be doing 2 or 3 or 4 different breakthroughs that you guys are going to be reproducing and bringing to the world within a short period of time.
Well, Drew and Charlie Bueller, they're getting consistent results and their work is moving forward, right? Like the Meg that Curtis is working on, they are moving forward with that. We have 5 or 6 different projects that are moving forward. The Graviflyer, it's like they're producing all of these effects that he's looked at. And then you have other things that are further out there, right? Like Isaiah Ritchie with the SEG. That's something that may be a little longer term, but so yeah, it is exciting, and I think this is like the time to really start working on this. I was just reading about Starship yesterday. I mean, $23 per pound to orbit. So, we're just about there. I mean, that's what they're looking at in the next few years.
We can do a Kickstarter and raise enough to send all our experiments up.
Yeah. So, anyhow, I didn't mean to jump in and proselytize, but did anybody else have questions for Mike?
Yeah, I don't even know how to form this question though, but you were saying that the Earth as a giant mass isn't what's creating gravity on the Earth. It's some kind of harmonic,
Electrical
whatever.
resonance. Yes.
So, well, gravity is based on
The two are interrelated.
electrostatics or electrodynamics, or what gravity is like some EM field?
Yes, it's a cross product. You guys before here were working along the same lines between your gravity and electromagnetic. What was it, Jim, or whatever you had? They are interrelated.
No, our work is electrostatic, and it has no gravity component at all, as far as we know. But
No.
So okay, that's cool. I just all the textbooks say it's you get enough mass together and it warps space and sucks things in. You're saying it's the electric field that's generated by the mass? What if there is no electric field?
It's the electromagnetic field generates mass, not the other way around. Mass doesn't generate the field generates the mass.
Okay.
That's my opinion.
So if I have a block of something that doesn't have an electromagnetic field, it doesn't weigh anything?
Well, everything's got an electromagnetic field.
It does?
Pretty much so.
Okay.
Yeah.
Sure.
Well, and let me see. We're about 20 minutes out from 4. Does anybody else have questions for Mike? Okay, well, why don't we do this then? So you know what? Why don't we go to lab time next? And Dan, I have not forgotten about your video. Maybe we could put that in like the open discussion part later. But Curtis, go for it.
Yeah, I uploaded a PDF of my slides, and if you want, I can just really quickly show those so that anybody watching this video can, jump ahead and.
Yeah. Let me do that. Well, so let's do this. Let's go to lab time, but we'll get that in there. But before we do that, again, one more time, a big hand for Mike Gamble. Mike, thank you for presenting. Yeah, it's exciting. It is exciting, and it's getting a lot of buzz online. So it's nice to see people digging in and trying to unravel it. Okay, and so Curtis, let me do this. I'm going to put that up, and I'll. I guess if we're going into lab time, I'll just leave everybody up on the screen. Is this the one you were? Yeah, this is the one that was blacked out, right? Oop, and you're muted, sir.
Yeah, that's the one that was blacked out. Sorry about that. So again, this is a standard formulation of E&M, and here we get as I said before, you can reformulate it in terms of a spinner kind of quaternion formulation, as I like to put it. So you have the fill terms and the source terms on the right, and you get you can set up an equation. This is a set of equations where alpha is 1 and 2, so there's 2 sets of equations, and it'll give you using the below, you can recover back Maxwell's equations. So those are the slides that messed up earlier. So if anybody wanted to see this, that's it.
Awesome. Thank you. Well, yeah, so I guess we can go and do lab updates now, if anybody has lab updates. And we're missing, let me see, it looks like Mr. Sokol and Jeremy Reese, some of our usual suspects are missing today, which is totally cool. But
yeah, I got some stuff, Tim. I'm just trying to sanitize the slide so I can throw it up on the screen for you real quick.
Okay. Well, Drew, let me try and spotlight you. Oops. I want to be careful. What's that do? How's that for scary? What's that button do? That does solo layout.
Sure. Hi. Drew, sunny Florida.
Drew, do you want to do a screen share?
Yeah,
when you're ready. When you're ready.
Yeah. Me and technology don't get along. Again, every one of these programs has a different. Oh, I guess this is called present. Is this called present? Oh,
yeah. So click present, and then you could do. I believe there's share screen. Yep, share screen. You could do Chrome tab or window or entire screen. It'll let you do.
Okay, yet more buttons to push. Let's try that one.
It'll make you.
Did it happen? Y'all see a screen?
Voila! I do see a screen.
Okay. This is a real typical experiment. As you can see, its runtime is along the bottom. Those are in seconds, and that's real-time seconds. So this was, I don't know what 12,000 seconds is. It seems like it takes hours to go by. But basically, what I do is there's 2 plates in the system. As you can see, the vacuum is whatever 10 to the minus 6 times 10 to the minus 6. And I don't wish to argue with Curtis about vacuum, but real vacuum doesn't start till 10 to the minus 6. Anything above that is you're still in the realm of plasma. You're in the realm of air pressure. I mean, if you really want to see if you're making thrust or if you're getting lied to by your toy, then you need to be down around 10 to the minus 6. Everything else is there's just so many ways that the mischief can. There's gremlins. The gremlins live above 10 to the minus 6, and 10 to the minus 5, you better be down around 1 or 2 10 to the minus 5.
I agree with you, Drew.
I'm just telling you, I've been down this path. I've seen digital force meters working at 10 to the minus 4, where they pick up on the harmonics of the EM field that's being generated by the capacitors in the system, and you'll start seeing false forces, and then huge false forces like 5, 6, 7, 8, 9, 10, 12 millinewtons of force, and you're thinking, wow, man, this is great, this is just the most amazing day, and then you realize this ain't real, because you drop the pressure and boop, all your magic goes away. So anyway, I'll get off my soapbox now. Basically what we're looking at here along the bottom, and I don't know what I'm pointing at, so I'll just point at something. Along the bottom is 2,000, 4,000, 6,000. Those are seconds. And what I do is and I'm just messing around with the parameters here, is I'm trying, basically I shut off plate A because it was having some kind of mischievous unhappiness. So this is all basically one plate. So this plate weighs somewhere in the zone of around 300 milligrams, which means if it were to generate something on the order of around 3,200, 3,300 micronewtons or 3 millinewtons, it would be at Earth unity. This particular plate didn't get there; it only got up to around 2,000 micronewtons. But it did open a whole new chapter of awesome for Charlie and I, which actually forced Charlie to put down his beer and sketch out some stuff and then email it to me, and then he went back to his beer. So what we have discovered is the forces that you see here. If you'll note, let me just tell you what's going on here in the red. I don't know where to point. The red going up, you can forget about all the dotted red lines underneath the center line. That's a figment of my new software display, because we've switched to a positive and negative power supply, but only the negative power supply is operational. So only the bottom dash things are real. The top red things are basically phantoms. So the power goes from 0 to some negative voltage, like -8, like -7,000 or -7,500 or -8,000 or something like that. So all of the dashed lines along the bottom are real. All the red lines along the top are a figment of the program, which we haven't figured out yet. So when I switch on the high voltage, obviously the voltage drops and the thrust goes up. So it starts at 0 and works its way up. You'll notice that I turn the voltage on and off, 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 because I'm working different parameters. I'm changing electrical wiring. I'm changing all kinds of stuff on the switch panel. And you'll notice that the thrust keeps climbing, even when mostly when the system is off. And that's kind of important, because what we figured out is we're actually running the system, we're actually injecting charge into the plate, and it's penetrating into the dielectric, not very far, but it is going in. And then when you cut the power, the charge is already in there, and the mirrored charge comes up from the Earth, and all of a sudden, you don't have any field going all the way across to the other side. You have a little microcosm of trapped charge and the metal plate right behind it. And you think, what's he babbling about? The point is, in order to make thrust, all you need is a massive electrostatic field, which every electron or every positive hole has the same electrostatic charge as every other one. So if you pack up an infinite number of charges inside your material and you put a ground plate right next to them, there's a hellacious field across that little gap. And that gap's only a couple of microns. So what we found out is that when you turn off the power, and we've known this for a while, but this is the first time we've actually displayed it. When you turn off the power, all you're doing is turning off the big field, the one that jumps from this plate all the way over to this plate. And now you're seeing the little field, well, you're seeing the off power field, which is all little tiny charges that are trapped just a couple of microns away, and they're generating a monster field. That field is so strong that it's able to produce thrust. And in this particular case, because of a little quirk in the physics of materials, this is some part of our propulsion called the divine force. The forces flip. So when you turn off the power, the thrust goes in the other direction, but it actually climbs because you're sucking in more and more and more charge. And the net result of all this is, as the hours go by, I was packing up more and more and more charge in the system. As you can see, the black line is constantly climbing higher and higher and higher. So you get to the far right side, and you see when I turn on the power, the thrust drops about 300 micronewtons. You turn off the power, and the thrust goes up. Back up, and it always goes up a little more than it was before, because while it's on, you're packing up charge, and it's just very cool. I ran this thing again the next night and the night after that, and I got it up to around 2,000, 2,700. I can't remember exactly how high up I got it, but I got it right at about 90% Earth unity, sitting there in a vacuum chamber, off. I mean, off, like in all of the little wires were disconnected, and it was sitting there with the turbo pump on for 12 hours, making thrust. So that was kind of cool. That was kind of cool. And now we're just going to scale it up and build a 1 pound thruster or 4.5 Newton thruster. It's going to be on the same exact plate technology as this, because it turns out that 4.5 Newtons is the minimum amount of thrust you have to make in order to get anybody that has a lot of money to listen to you. So that's our next goal, is 4.5 pounds. That's it. That's all we got going on here in sunny Florida. Questions?
I got one for you, Drew. Are you planning at any time on doing some independent party vacuum chamber testing, like NASA Goddard Center or something like that?
No. I don't believe in NASA. I think they're a figment of some deranged situation.
No, they are
Dude,
real. Dude, they are totally real. I've seen, they have like buildings and stuff. I've seen buildings.
Yeah, I worked out there for 30 years. I still work out there, but no.
Kepler Aerospace would be another one.
There is nothing NASA has that I don't. I have chambers that'll go down deeper than they have. I have a better understanding of what's going on, and I got the smartest dude there is on my team for electrostatics. I got the dude who figured all this mess out. So no, I have no intention of bouncing a third party off of anybody.
I think Kepler Aerospace has like the world's best vacuum chambers for how fast they can pull vacuum, and I think they can go down to 10⁻⁶, and they're transparent, like totally transparent.
Oh yeah, you can go down fast. I mean, I've gone down to 10⁻⁷ in my chamber, but there's no point. As soon as you spark, because these things are made out of plastic and various polymers, and if you spark for just boop, one little tiny spark, boop, you're back up to 10⁻⁵, and then you got to pump down for an hour, and you're talking atoms. You're talking millions of atoms difference between 10⁻⁶ and 10⁻⁷. It's ridiculous. Plus, it's all subjective. Once you get down around 10⁻⁵ times 10⁻⁶, these things all behave very nicely. You stop arcing. You stop generating. The charge stops jumping up and over, and by some little air bridge or whatever. So it's a lot more fun. So yeah.
Well, I mean, Jared, he has a good point about NASA. I mean, Charlie is the electrostatics person at NASA, right? So, to take it to NASA, basically that's just his partner going into work every day. I mean,
I was just more going along the lines on independent testing in other facilities.
To what end? I get asked this question all the time, especially by the money guy on our team. He's like, "Hey, let's go to Boeing. They're willing to put our toy in their chamber and test it." And the answer is, first of all, I don't trust Boeing. Secondly, I don't need Boeing. And thirdly, I don't want to ship this thing all the way out there and have them break it like the last time I did.
Yeah, well, I don't think anybody trusts Boeing this week. Not after the last.
Well, yeah, what happened with that dude?
I don't know, but I do not want to cast aspersions, especially against giant litigious mega corporations. But I just saw a post on Twitter. Supposedly, he said, if anything bad happens to me, it's not suicide. Like right before he committed suicide. So
back of the head 3 times.
If anything bad happens to me, it was not suicide. I love life. Yeah, I intend to walk on Titan one day on my own spaceship.
Yeah, so I don't know. But then on the other hand, it seems like it would be incredibly obvious to do something like that. You know what I mean? But who knows? The mob used to do stuff like that, so I don't know.
Yeah, no. So that's all I've been doing. I'm trying to find out how to stop sharing. Maybe that's it.
Oh yeah, it should be automatically stopped shared.
Okay.
And yeah, does anybody else, Jared? Do you guys have any lab updates you want to share? Or? And I don't see Charlie with us.
Phil's got
Just
something.
Phil has a lab update. Phil,
Jared,
what
I
do you
want to
got?
hear about that Graviflyer.
All right, I
Okay.
can give a short update. So recently I noticed how these vertical rods, we'd been dealing with ones that were too long. And I went back through, I asked Mike to give me measurements on the rods on Alexi's, and then Charles has another one that Alexi built for Russell Anderson. So we checked on both of those, and then I went through Alexi's videos and did pixel by pixel measurements on those. So I got a really good idea, not just for the length of the rods, but for the positioning on these cross members. And I already knew that the square root of 2 shows up in all of the spacings for the discs. But once I got the rods in there, I put it into a spreadsheet, and I was starting to look at, are there any other root 2 relationships going on? And they just popped out left and right all over the place. Like the distance between the spacing for the cross member to the center disc compared against the spacing to the top of the rod, right? Stuff like that, right? And there was like 4 or 5 different ones like that all over the place once I took the rod lengths into account. It's an interesting observation because root 2 is what you're dealing with when you're doing power transfer stuff, RMS voltages and that kind of thing, RF transfer and that sort of stuff. Anyway, so that was the one big thing. The other big thing was, like I already shared, about the pulse factor on the ultrasound. So I've been starting to try to incorporate that into the working theory behind the Graviflyer. There's, half a dozen different theories on how this thing works, but the one that I picked up from those pulses was that it looks like the skin depth in the center disc is a very important aspect to look into. So the RF coming from the Tesla coil into the center disc, that's at about 70 microns, 70 micrometers. And then the frequency of the ultrasound, Alexi, when he did his live lifting in front of us, he said that it was running at about 91 kilohertz. So I started plugging in these numbers for the ultrasound and the Tesla coil, and I started noticing that the skin depths were ratios of each other, right? So the skin depth of the ultrasound compared to the Tesla coil, it was like 2 or 4 times the amount, right? So when Alexi says that he wants to make it go up higher, he says that he has to turn up the ultrasound frequency. Well, when Charles does that on the circuit, it shows that it's shortening that pulse time, right? It's shortening that rise time. But also it appears as though that skin effect, that skin depth, is also going to be going in integer amounts of the Tesla coil skin depth. And what I think that's doing is it's like forcing these currents. There's an eddy current in the center disc from these spinning magnets and everything, right? So what it's doing is it's taking this layered eddy current and it's squeezing it all up towards the surface of the disc. And when you do that, you're starting to increase the field strength. So that's last thing I got is there's a YouTuber goes by the name of Old Man Builds, Nathan Bunton. I've gotten in contact with him and had a couple meetings with him. He has been working on the Graviflyer independently for like the last year and a half, something like that. And he has a lot of really good insights as well. Very excited to get to be working with him now.
That's awesome. That's awesome. Yeah, it is interesting. It grabs you, right? I think Mike had said that. Mike had said that to me. He's like, it grabs your brain and then you can't get away from it. So.
Well, you've got a new convert over to your Graviflyer madness. It's not me, but it's somebody on my team.
Wait, your team is you and Charlie, right? So
that's pure madness. Okay, that's the whole spinny thing. That's just pure madness. So I'm not going to work on it.
One other comment. Somebody had mentioned Hutchinson. It might have been Curtis. I forget who. Anyways, the difference though between Hutchinson and Alexi for their magic tuning thing is that Hutchinson, it takes him like half a day, sometimes multiple days to get an effect because it's a random nonlinear thing. And it just so happens that it gets into the thing and it makes the effect. Some effects he could get when he wanted, but most of the levitation effects he couldn't get on command. It was like hit or miss nonstop. Alexei, however, he can make it lift. It takes him 3 tries on average, but he can make it happen, you know, and at 45 to 60 minutes per try, he can make it happen in 3 hours, you know, pretty regularly. So props to Alexei for, you know, having that artistic touch of being able to make everything work, especially considering that he's not using any measurement equipment at all.
Yeah, but
Hey, when you said live, you mean like you were in a room with it when it was happening, or you just watching it on video?
Zoom call, live Zoom calls.
Okay, and during a live Zoom call, he got that thing of his I thought that guy, Mike said it was the unit that was sitting on his desk. Did he ship it to him, or
he shipped it? Yeah, he shipped it in.
He's built a few of them. In the first Zoom call we had, he had just finished building it, hadn't even really tuned it much, tuned like spacing and stuff, and he was very excited to show it off. He's like, "Hey, here, let's see if I can make it, you know, do the thing." And after 3 tries, he got it to do the tilt over thing that it does when it's not tuned well. And then in our follow-up meeting 2 weeks later, he did it again, and that time he was able to get it to actually lift. Unfortunately, because the EMP that is released when it lifts or when it tips over, when it does the thing, it makes all of the electronics, like the camera, start going wonky and haywire. So immediately after that meeting, we had him use his iPhone camera to do it, and he was able to do it again.
You didn't secretly recorded the meeting?
We recorded all of those meetings with him. We are not making them public yet, but we hope to be making them public sometime in the coming future.
Yeah.
Awesome. Well, that's great.
Well, Jared, thank you.
Upon his approval,
so now that Phil has spoken, Phil has to update us. That is the Phil rule. Phil, now that you have revealed yourself, you must give us your update.
Yeah, I was hoping to be done tonight, but I just have a minor thing to fix. I need to get some conductive glue to stick metal plates together. But I'm a week away from being done from everything. I just got, I had I was using this cover before, as you can see. This cover, it was leaking, obviously, because there are big openings. The gallium was leaking. Now I just got the new cover. That is not leaking anymore. So there are slots to put in the electrodes and everything. So I've got the electric system powerful enough to go to high RPMs. I've got the cover. I've got the magnet. I've got pretty much everything except the conductive glue, which should get early next week. So I'll be able to do the experiment next Wednesday. I'll record it, obviously, and I'll scale it up at good old University of Sherbrooke. But I'll do it at home before, and I'll share it on the chat next week once I'm done. I'll show it at Mike Faraday's show or something like that, and or the lab, APEC lab update in 2 weeks. But yeah, I'm almost done. I was hoping to be done tonight, but unfortunately, I missed the boat tonight. But I'll keep you up to date. I'll send it to the chat and everybody else. So yeah, I'm pretty excited, and even if I just had the cold like 2 times, and I'm still pretty excited. So yeah, so that's what I want to share.
Okay, well, Phil, thank you. So guys, I think that's probably it for lab updates, right? But I have that presentation from Dan. Dan, I found your Dan recorded it a couple of times. I can play that. That's about, let me see, exactly 30 minutes long if you want. Or we could go to open discussion. So, okay, well, why don't we we'll officially call this open discussion, but if you guys are cool, I will put up, and let me see if I can do this without destroying my computer in the process. Okay, present. See, I have problems with it too. Although that being said, StreamYard, it truly does grow on you after a while. It's just really fluid. So
does it broadcast on Twitter and also social medias?
Yeah, it does on social. I don't have it set up to broadcast on social. What I am gonna do though is because I always download I download a copy of the stream, back it up. I'm gonna create video shorts and put those out over the next week, and I've started doing that. So yeah. Okay, well, so I think here, let me see. Yeah, you guys can see that. So what I'm gonna do is I'm just gonna start playing this, and I will maximize the screen. There we go.
Okay, so today we're going to be having a talk about the interpretations of quantum mechanics. Because it's become very clear to me that some of you have stated that it doesn't matter which interpretation that we're using because they're just philosophical interpretations of the same theory. And that's not inherently true. I'm going to show today how they do lead to different outcomes in their predictions, and how they are. Many of these different interpretations are distinct theories, and why one particular theory amongst them should be the one that we should probably be focusing on. So now I'm going to give the caveat that, much like my warp drive talk last time, that this is going to be a qualitative exploration, not a quantitative one. And that for the PhDs in the audience, I am going to be some notations here that are wrong. That is somewhat by design. We can get into that afterwards. I'm trying to bridge the gap between you guys and then the rest of the audience, to express that these ideas are accessible to everybody. And so some of these notations and things that you guys might notice are going to be wrong. Just notice that I realize that, and it's more for the visualization of trying to give a broader understanding of what's going on here. So that being said, what do we usually mean when we are talking about quantum mechanics, right? Some people say, the general relativity is the theory of the very large, and quantum mechanics is the theory of the very small. Well, that's not precise enough for me. So what we mean is we're talking about the Schrodinger equation, right? So what is the Schrodinger equation? It's the Hamiltonian operator of the wave function h of psi equals the energy of psi. So you could write h psi equals E, of psi. So what is E of psi? We can say that is I h bar d by dt psi. So this is how the psi is your wave function, and it tells you how this wave evolves throughout time, which is your t operator here. So what does this mean? This is literally Greek to me, right? So we'll keep this up here just for kind of, keep it up in mind. I'm going to draw a quantum harmonic oscillator, a version of it. So we're going to start out with our well potential here, and we'll just start with our two system state, and we'll say it starts at a superposition where our starting state of psi 0 progresses in time to psi 1, and we're going to say that this is A plus B, and then A and B. So, excuse me. Sorry. So, as the wave function, the wave, evolves with time, this Schrodinger equation tells us how this wave spreads out. Well, what does quantum mechanics say? It says that the world evolves according to the Schrodinger equation when we're not looking at it. Now, when we look at it, it does something different. It collapses to a particle, right? Because we don't see waves, and we see, well, we don't see the wave function. We see particles, right? So this is what's known as the kind of a textbook quantum Copenhagen interpretation of quantum mechanics. Excuse me. So how do we get from waves to particles? Well, we have to make an observation. So this system evolves according to the Schrodinger equation. It starts in, at A plus B. We'll have a coin right here. We'll say that heads is A and tails is B. There's going to be a 50% probability between these two. So we can rewrite this by squaring the wave function. So we have 0 square and psi 1 squared. So we're going to have A plus B, and then these turn into probability amplitudes. These are the probability, the chance that we might observe one of these two. So A plus B. But, so if we're going to say that heads is A and tails is B, let's flip the coin. We're going to say that it's tails, so we know that the system evolved into B, okay? So what happens is we would, just erase this. This is what Copenhagen says. What happens to it, we don't really need to worry about it because we observed it. So then we reset the system, and then we just kind of keep doing that coin flip toss each time, right? So we could say that the system over here, psi 0 is equal to A plus B, and then as we evolve the system, it's 1 divided by the square root of A plus 1 divided by the square root of B. And then we did our coin toss. We figured out that the system was B. And so now we erase this. And we erase A because it wasn't the one we observed. So we just make it go away. And we renormalize to say that B is now our starting state. And then we evolve it for whatever we're doing for that particular, whatever we're assigning B to. In our, whether it be another coin toss or what have you. Now, the reason that a lot of people say that that Copenhagen is incomplete is because we just say don't worry about these other worlds that everyone we didn't observe, right? We don't need to worry about that. Now, there are other theories like Penrose, which give a reason for why the one might collapse to the other. So what Penrose theory states is you have the time towards the collapse. It's equal to H bar divided by the gravitational energy of the system. So what the hell does this mean? You might notice that actually this looks a lot like the Heisenberg uncertainty principle. That is somewhat by design. But this is not an in-depth thing on Penrose. So let me go with here and here. So what the hell does this say? Let's move this down, and we're going to start with our system here. We're going to have 1 going off here, and we're going to call this B. We're going to have going off here. A, we're going to call this A plus B. And so there's going to be some gravitational self-energy between the system. This will be a larger well, and then this will be a smaller one associated with this one. And the collapsing happens when, because remember it was T H bar divided by E G. So another way that we can just say this is that when the difference of the weight between these two, or just, you know, the difference between these two adds up to become greater than or equal to H bar, is when the decoherence or the collapsing of the wave function occurs. And which one does it go to? Well, the one with the larger probability. So that's, excuse me, sorry, I got this cough going on. So that's Copenhagen and Penrose in a nutshell. Okay. Well, what else do we have other than Penrose and Copenhagen? We could do something on, not GRW, I forget what it's called, but a very reasonable question to ask here is, why don't we just start with a squared wave function? Modify the Schrodinger equation so that we don't have these other things, and we're just going to put the Born rule right into it. Well, what we find out is that when we do this, it changes the predictions that the theory starts to make. Now, what are some of those predictions? Well, we need to think about the difference between waves and probabilities. Waves can interact constructively or deconstructively in how they interfere. Whereas probabilities only add up. So if you're only propagating probabilities through time, they're only going to add together. You're going to ruin the interference patterns of the deconstructive interference that the wave part of the equation is going to predict. So that is why certain theories like that people have tried and are still continuing to try don't necessarily work. So that's Copenhagen, Penrose, GRW in a nutshell, right? So what's something different that we can do? Another one that people really like to play with is like Bell's theorem or pilot wave theorem, or hidden variables. So what are those? So I'm just gonna get rid of this here, and we're gonna keep our Schrodinger equation at the top just for posterity here. We're gonna make our we're gonna say this is our wave function. So our wave function evolving according to the Schrodinger equation, right? Then, remember, because we don't see the wave function, we see particles, right? We have our particles. Here, this is what we actually see. This is the world we're in. We don't see the wave function. So we have a wave function and our particle. Well, what pilot wave theory suggests is that the particle is guided by something called the guidance, or the pilot wave guidance equation. So what is that? It's V equals H bar divided by M I plus Laplacian of psi divided by psi. I can make that one better. So this is pilot wave in a nutshell, and this is a valid theory. It's a valid interpretation of quantum mechanics, but we're noticing that, again, these aren't interpretations of the same theory. These are different theories. So how is this a different theory? Well, what we find out is that this interaction here, this extra equation between, adding in the particle instead of just the wave function, in the Born rule, it will start to change the observation, you know, the experimental predictions that you would get from just doing Copenhagen. And so again, we start to see that they're, you know, much like just trying to square the wave function, you know, to start with a squared wave function and evolving that instead of evolving a wave function and then squaring it. Again, these lead to different these lead to different, you know, predictable outcomes that don't necessarily line up with each other. So again, this is why they're not inherently all the same theory. Okay, and so there's one more we can touch on too. The last one that we're going to touch on out of these main interpretations is the many worlds interpretation. So what does the many worlds interpretation tell us? It tells us that there is a wave function evolving according to the Schrödinger equation. And that's it. No collapse, no observation, no measurement, no spooky weird quantum woo, no guidance equation. This is the simplest, most austere version of quantum mechanics, but this comes with implications of its own. That being, you know, many of you might know the Everett the Everettian relative state by its other name, the many worlds interpretation of quantum mechanics. So the many worlds is what we're saying, that just the wave function is reality, and so that these other branches do exist. They just decohere, and we don't see them. Now, this is where Penrose can come back in with his theory. Because if we're doing the h bar equals 1 equals c, and at the time is h bar divided by e, this is basically just we can play with the term. We can play with the terms around a little bit to say that the decoherence happens faster than the speed of light, which is why we don't see the branches. So Penrose was right there in the wrong context. He made a decoherence theory instead of a collapse theory. So that aside, why might someone go with this? Well, again, because we're starting with just the Schrödinger equation. That's it. Now, the Schrödinger equation and the evolving wave function is a robust feature of each version of quantum mechanics. So while Occam's razor, dictates, that we want the most simple theory, well, this is the most simple theory in the assumptions. We're not putting the other worlds in; they just are part. They're there in the wave function. So let's talk a little bit about quantum gravity now and why somebody might want to go with the many worlds interpretation versus the other ones. Well, the people talk about that the quantum mechanics and general relativity don't jive. They don't work with each other. So there's a couple of reasons for this. One is that this actually isn't a relativistic equation. We would actually have to turn this into something like the Dirac equation. So we could say I gamma mu minus m psi equals 0, or something like the DeWitt equation. My marker's starting to die a little bit. H of psi equals 0. These are still, so that this is an appropriate version of the Schrödinger equation. So, the saying relativity doesn't jive with quantum mechanics in one sense. Okay, so we have the one covered. So let's just get rid of these now. We don't need to worry about them for this talk. We'll just keep them in the back of our mind for later. The other reason is this renormalization mechanism. That might not be the right word. Sorry, I'm struggling with this cough a little bit. The whole process of, starting here equals A plus B, and then here goes to, see, my marker's starting to die, equals so this is still kosher. Actually, so this is probably a quick segue into what the Born rule means in the context of the many worlds interpretation. The Born rule is just the relative weight of each node of the splitting branches of the wave function. So this is still kosher so far. Where general relativity has a problem is in the quantization mechanism of saying, when we flip a coin, we say this, this time it's still tails. So our system evolved into B. So these go away. And then we now start our system back, saying that process right there is where general relativity does not work. That does not survive that quantization mechanism. Now, that leads into the natural question of, in Everettian theory, where you don't have the observation and you just have the wave function evolving according to an appropriate version of the Schrodinger equation, what about then? Well, we find, surprisingly enough, that general relativity was hiding there the whole time. So, how do we do that? We're gonna redraw this picture a little bit. So, this is not the only way we can think of a quantum system. We can also think of a quantum system as a qubit, right? And so in our qubit here, we're going to say is a sphere, and there's going to be some state here, a radius r at some this r as some elevation angle and some azimuthal angle. And we'll say, that this is spin up and spin down. This is where the Dirac equation starts coming back into play, but we're not going to do a deep dive on the Dirac equation today. So, just like any point in this is called a Bloch sphere, by the way. Any point in this Bloch sphere can be assigned with a state in our evolved Schrodinger equation, right? So we find out, where does general relativity start to come into play here? Well, this is through entropy. So what is entropy? Entropy is just the maximum amount of states that can be. Now, what is the entropy of our state? In a quantum system, we're going to say that S is proportional to the IR divided by UV, because traditionally in quantum theory it is stated that there is an infinite amount of possible states that each node in this quantum harmonic oscillator can vibrate in. Because now, why might we assume that a system would be a finite, and why would we get this? Why would we want to assume an area relationship with this? Well, because we know that if we counted every single energy state below a certain point, it would start to collapse. Again, because of the Heisenberg uncertainty principle and Schwarzschild radius, it would collapse to a black hole, right? And we know from Bekenstein and Jacobson and Hawking that black holes have a finite entropy. And what is black hole entropy? It is roughly equivalent to the area divided by, that's not the right, area divided by the Planck area. So you're counting the number of states that your system is in Planck areas, and that gives you your entropy. That should seem like a pretty natural progression. All right, well, we find that, let's erase this. Erase the Schrodinger equation too. Because S is proportional to area, our entropy is proportional to our area. How do we find? We can find Einstein here now, because area is some level of spatial curvature, right? So we're going to say R spatial curvature. And then through some more math, we can say that the spatial curvature is proportional to G00 proponent of the Einstein tensor. And we can say that entropy through entanglement can be associated with our modular Hamiltonian, which through the IR limit can be associated with the T00 proponent of the Einstein equation. And then through Lorentz invariance, we know that T mu nu is going to be proportional to G mu nu. So what is G mu nu proportional to T mu nu? That is just Einstein's equation, right? So we have just found Einstein is an emergent property of Everettian quantum mechanics. Of just our system evolving according to the Schrodinger equation. So how can we write this? How can we visualize? How can we help visualize this for some of you? We can just do it with a hyperbolic tessellation. We'll make one of these guys red. Bear with me here for a second. This will only take a second. And so what we find here is that these entangled states, as they overlap, we can count the number of them by counting all these states will be our entropy. And this is our area here. And again, just to try to put this picture back together, let's go blue here. Remember our globe sphere. There was some coordinate angle. In your spinner. And that is a pretty good visually. We're at 27 minutes right now. So that is a pretty good explanation of why many worlds theory is not just an interpretation of quantum mechanics. It is quantum mechanics, in much the same way that I guess sort of like how you would say that this is evidence of the multiverse, the quantum multiverse, sort of like how we're going to say that fossils are evidence of dinosaurs. We're not going to say that fossils are dinosaurs, but we can assign a degree of confidence to this theory as high as our confidence in something like the theory of evolution. would have. Now, what are some interesting implications of this? Well, we find out that faster than light travel outside of our particular light cone. Some people are going to say this is wrong because technically you're either skewing the null lines where you're rotating it, but we can just say that traveling outside of our line here is just representative of skewing or rotating, and really what the goal here is trying to get the causal light cones of two different universes to overlap. And then, through faster than light travels, how you would be able to bounce around between some of these different nodes or branches of the Everettian multiverse. And so that is probably a decent place to leave it. So we showed pretty qualitative here, not quantitatively here, how these different interpretations of quantum mechanics are inherently more than just interpretations. They are different theories, and how that despite some of the uncomfortable implications that come with it, the many worlds interpretation is probably our best bet. And in fact, I would go so far to say is that it's not the many worlds interpretation is the many worlds interpretation is quantum mechanics. I'm going to say that these other interpretations or these other theories of quantum mechanics are disappearing worlds theories is probably a more accurate and cheeky note to leave it on. So I guess we will go from there. That's the gambit.
Sorry, I'm still muted. Yeah, Daniel, thank you, man. You know what? Let's do this. Let's give Daniel a hand for putting together a tremendous half-hour pre-recorded presentation and recording it twice, right? That was your second run. So
yeah, well, the first one, the audio got butchered on it, so I had to redo it.
Yeah, trust me, I'm doing video, audio all day long. So yeah, I know where you're at. Well, yeah, thank you, man. And so yeah, I guess this is kind of open discussion. Do you guys want to maybe just keep it going for we could close things down in 20 minutes? That makes today a little shorter, but the sun's out here in Seattle, so I want to get a little bit of sunshine. And then actually, you know what? Maybe I should share this really quick. Yeah, here. This is not. I found this the other day. This is not related to APEC, but this is Alan's conservative countdown to AGI. And I guess some people are putting faith in this. They're saying that artificial general intelligence may be here in 7 months. And so if you just Google this, Alan's conservative countdown.
Some say it's already here, but for a public, for it to make itself public and available to the public, that's exciting.
Well, yeah.
I'm still waiting for biological intelligence. I don't know when that's...
If it can extrapolate and predict things, and it's going to be scary,
Yeah, that reminds me of that old, what was that Onion article? Congress, this was back in the 90s. Congress passes the Americans with No Abilities Act. So that was back when they had funny stories. But well, yeah. So yeah, open discussion, guys. Whatever comes to mind, and if we run long, that's cool. And if not, we can shut things down at 5 Pacific. So
Dan, I'd like to ask something.
Yeah.
Thank you. So would it be right to say that like a takeaway from your talk would be that Everett's quote interpretation? I mean, I realize that one of the points you're making is that it's more than interpretation, but just using the traditional language. So would Everett's interpretation, in your viewpoint, be the necessary quantum model for unifying with gravity?
Yeah, because you don't need traditional quantized gravity when you have entropic gravity. That's what this is entropic
Oh,
gravity.
that's right. That's
Yeah,
right.
so when you have emergent gravity like this, you don't need to do the quantization process for it at all.
That's right. That makes sense. And okay, that's a good point though, because I know that a lot of papers that basically communicate the problem of unification will often go to the Copenhagen interpretation, at least implicitly, when saying collapse of the wave function is going to introduce a discontinuity in the metric, which is not permissible, like in Riemannian geometry. And
Yeah,
so
it's not that general relativity isn't compatible with a wave function. It is compatible. It's an emergent from an evolving wave function. It's the collapse that doesn't jive with it. Now we can come up with decoherence mechanisms, but those are decoherent.
So you're really making a statement about gravity, not just about quantum. You're saying we have to have entropic gravity and we have to have Everett quantum mechanics.
And it's the most simple starting point too. And like there's a I don't have it pulled up here, but there's a paper by Dr. Yuri Eroshenko out of might be Russia, but it could be Poland too. I have to double check. But his paper, Escape from a Black Hole with a Spherical Warp Drive. I could probably try to find a link for you guys. Essentially, and he does have some math to support this idea, but basically he comes to the idea that warp drives are, in essence, non-instantaneous wormholes, and then therefore we can then equate the ER equals EPR conjecture into warp drives equal EPR. And so really what's going on here is that because general relativity is an emergent process from these entanglement structures, really what we're saying is that these warp drives and wormholes, they're really semi-classical descriptions of what's really some very complex quantum entanglement going on.
If you add metamaterials to that, Jack will give you a hug. We got ER equals EPR. You need to add metamaterials. Mix those together, and you get a hug.
That should look familiar when it comes to Jack's work. And I've been plugging it into Parisiano's modification of the Alcubierre metric. So yeah, no, I'm right there.
Yeah.
I hate to ask the obvious question, but how does this help us build a spaceship?
Because a lot of people in this field, right? They're speaking in a Straussian communication when they're talking about, hey, we know someone, quantum mechanics says X, Y, Z about science and this, right? And then they just start going into the theory upon it, and they're assuming some version of quantum mechanics, but they're not specifying which one, and whichever version they're using can make huge differences down the line, in your equations and like where your theory is going to head. So it's good to have the right starting theory.
Yeah.
So essentially, this isn't going to help us build a spaceship. This is going to help us explain why the spaceship flies after somebody figures out how to build it.
I think it helps guide.
So where this starts to become more relevant to the spaceship isn't so much the build. I think some of Jack's ideas might a little bit better on that, and you guys are more on the engineering purpose. I think where this starts to become more. Not more regarded, it's very required, is the navigational aspect. Once we do start going superluminal, with these things, because we gotta walk before we can run. We got to do subluminal drives first, but eventually, it seems like superluminal is where this is all heading, and we got to really be sure that when we hit that punch it Chewy button, that we're gonna end up 5 light years away like we're supposed to, and not 23 in the opposite direction because we didn't count for some sinusoidal wave that's happening on a trajectory that we didn't account for or something like that. You're right. It might not help us build the warp drive, but it might help us get a good starting point and then help us navigate once we build it.
Okay.
Yeah.
Thanks.
Yeah.
It's better to start with it. Sorry.
And again, I mean, I'm I cannot say how strongly I believe that diversity of ideas and experience and knowledge is so important. It's all about diversity. It takes physics, it takes hands-on people, it takes this entire combination of things. And like, go back to the movie Oppenheimer, right? He was working with the same thing. He was working with the physics, and then he was working with Livermore, right? So same thing. It takes a community to develop these things, and it always has. You look at what NASA has, right? They're working with rockets, but it's the same thing. They have theoretical physicists who are working on the propulsion aspects of things. They have hardware people. It's everything in between.
For sure.
Wasn't there an effort by NASA to replicate the Alcubierre drive?
NASA has dabbled in it, but to my understanding, the most they've ever really done is sponsor papers. Like Sonny's Eagle Works, that's connected to it. And
right now, Chance Glenn is setting up an experiment in the Buffalo University to run one there. He hasn't performed it yet. I'm pretty sure he's still building it. But he has a positive energy modification for the Alcubierre metric. Now we could get into why is issues with Alcubierre specifically, but that was my last talk. But Chance Glenn, he's using like a lossy dielectric cavity and then pumping RF waves through it to try to see if he can change the permeativity and permeability of the dielectric there, to see if they can get some kind of low level tabletop space time warping in the material. So that he'll be someone to keep an eye on in the future.
Okay, but isn't it coming down to generating negative energy or something like that?
Well, yeah, so that's one of the issues with Alcubierre, is that it takes, well, is it astronomical, levels of energy. I think it's like 10 times the amount of negative energy required for the observable universe. But there's been so many modifications. There's been 30 years of people tweaking the solution to the metric and getting down the energy requirements. And people have now found positive only energy ones. And then really, if we wanted to get started and get pedantic with things, we could go down to the side of the rabbit hole with saying that Herman-Boundy's positivity conditions that we all rely on today to say that, hey, we can't have negative mass because general relativity says so. Well, that's kind of an arbitrary choice that was put on by Herman-Boundy in 1957. Now, it might still be valid. I think we're better off pursuing positive energy warp drives, but I don't think we should fully count out negative energy yet either.
No, yeah.
Yeah.
And you said something that actually caught my attention. You said that it's possible to change the permeativity of a material with some kind of a field change, or did I misinterpret that?
Well, that's going to go into your metamaterials thing, right? Doesn't that kind of come back to that whole idea?
Yeah, I think I've actually done that, and I'm just trying to find out if what I'm seeing is a weird little quirk of my physics or a bigger quirk of the bigger physics.
No, there might be something to that. If you look up Chance Glenn and just positive energy Alcubierre drive, and you Google that, the papers should come up, and then he starts to get into like the experimental design that he's doing with it. He calls it like lossy dielectric, with a resonant RF cavity or something like that. It should be pretty easy to find.
Yeah.
What
Chance is presented here too.
I
don't know if you remember, Drew. Chance Glenn is presented here. Yeah, I'm really big on community building, but again, part of that is because like when I got into this like around 2000, and you look at a lot of the older fellows, they came up in a culture of like not invented here, and there was like this hierarchy, right? Like I do this, and therefore I'm higher on the ladder than you are, and maybe in their particle accelerator, maybe that worked, but when you're trying to develop new things, what it does is it stifles innovation and it hurts people. It's just it's like an old school 20th century factory approach, and like with physics, like I keep hearing this phrase, shut up and calculate. That was the old approach to physics, was shut up and calculate.
That's actually funny that you bring up that shut up and calculate, because that was first put forth by Feynman, right? He was a big proponent of Copenhagen. Well,
that's a new approach.
Max Tegmark, he just put out a paper he titled to "Shut Up and Calculate" is literally the title of the paper, and he takes it out to an extreme in favor of the Everyden principle. And it's interesting to see how you can take that argument both ways, you know. So it's not really an effective argument.
Yeah, I
would say, Tim, that's a new approach. That's not the traditional, you know, that's not the stuff Einstein and Maxwell were doing, and all, you know, everyone before that. Before
my entire approach. I mean, I came up in the tech industry, you know, and I did the .com boom and stuff, and one of the things that I saw, this is just maybe it does apply, but you had people from all different disciplines, and it was like, if you could use a keyboard, you know, this was Redmond, right? Redmond in like around 2000. If you could use a keyboard, all of a sudden you're in charge of X, Y, and Z, and like it came down to what made it work or fail was collaboration and teamwork and valuing each other, you know? And I mean, that's just so incredibly important. And that's one of the things that excites me about this conference is it doesn't matter where people are from. Now, some people have more knowledge and experience. Some people have, you know, more of an inclination to it, but yeah, I know. Sorry. I know I'm giving you guys
I want to pitch out an idea. Let's say I have a material, a polymer, and I subject it to a very high electrostatic field, say 10 to the 8th. Is it possible that the permittivity of that material can be changed by that field, such that while the field is on, say it has a permittivity of 2, and while the field is off, it goes back to its native permittivity of, say, 3.5 or 4.5 or something like that?
The permittivity of a material is going to greatly depend on the structure.
Yeah.
And it could be nonlinear. There could be breakdown in things. So you got to really look at condensed matter physics.
I'm going to say there's a non-zero probability of it.
Yeah, nonlinear material.
Yeah.
Well, and wouldn't that kind of
materials is changing because of the stresses that are put on it?
Yeah, as it breaks down, it can start to change the
And if it's a polymer, you've got additional flexibility, right? I mean, so you may have, I mean, because you've got those long, you know, CN chains and all that stuff in it. So yeah, it seems like it would be more susceptible to that.
That's what I'm saying. I'm actually changing the permittivity of the material by increasing the field. Yeah. And if you take that to the extreme, I think that's what the aliens are doing with that super magical metal that's got all them layers of bismuth and tin or whatever.
Eddie's idea is talking about is changing the permittivity and permeability in metamaterials to do exactly that. I mean, that's right. Literally what this equation right here is for, is plugging that into the scalar constant there to replace C.
If we could drive the permittivity to, you know, near zero, I'm not saying you can go negative, but, you know, let's say you can drive it to near zero, then our propulsion system goes orders of magnitude. You know, right now we're playing with permittivities around 3, 2-ish, you know, Teflons, Kaptons. But if we could drive that down to 0.2 or 0.1 or 0.3, then we go up by a factor of 10 squared, I guess 100. We go up by a factor of 100x. So,
well, one of the things Jack has talked about is changing the speed of light in materials, right? Which might be related to that. But then what's intriguing is, you know, and you're taking that a step further, and you're saying that, okay, you know, the speed of, you know, I mean, just hypothetically, what you're saying is that by stressing the material, you can further change those properties, you know, right. And that's not, I don't think that's in any textbook. I mean, the stuff, and the reason I mention that is when Jack was talking about that, one of the things that he had said was people forget that the speed of light is different inside of materials. That's considered rather esoteric knowledge, right? It's documented, but it's not well known, not like regular speed of light. Well, okay, in a stressed material, how much further different is that? How much more arcane? So it just seems like that opens a lot of doors, you know?
It might also be worth observing birefringent media.
Sorry, Jared?
Just a sec, Dan. I was going to say, Drew, you can have birefringent permittivity, right? So
I don't know what that is. What does those words mean?
Birefringent is like you take a cubic lattice, right? And you stretch it. So, now it's, slanted cubic, right? So what that means is that a wave going through one way versus a wave going through the other way is going to operate differently. So birefringence is normally talked about in optics, and it's usually not a great thing. You're trying to avoid birefringence most of the time with optics, but with birefringent media, even quartz is birefringent, where if you take a transparent piece of quartz and you put it over a graph paper, you'll see that the lines on the graph paper are like skewed, right? So what I'm getting at is you might be able to find materials that have certain birefringent permittivity properties, where when they're under certain stressed conditions, the ability for electrons to go through it are going to be different in one direction than another direction. And in that case, it's just point the thing in the direction so that you get the optimal lowest permittivity.
That almost seems like that starts to move it back towards the Meg and Woodward's work.
That's very intriguing. Thank you.
Well, by the way, Tim, you've been bringing up Jack's theory, and I know also Dan did as well. Have you guys been keeping up on some of the suggestions that were made to him lately? I've been corresponding with him, and an idea came to mind where I was trying to think about the simplest way to test that theory.
You talk about the
experiment
he's trying to do?
Yeah. Any
What?
thoughts on that, by the way? Because it seemed to me that's the simplest way of checking to see if the electrical properties of a material truly determine gravitational effects, which, I mean, I have got my own sort of opinion about that, but it just seemed to me like, yeah, if you have your Cavendish balls and you change out the material for a different material, but it's the exact same mass, what Jack would call passive mass, but different what he would call active mass because of the S quantity, which in this context would be essentially the electrical permittivity has been changed. Then the acceleration of the two balls relative to each other would change. And so the theta that you would measure in a given amount of time would be different. It seemed to me like that's such a straightforward experiment that could be done on a low budget, I bet. I mean, they literally sell like on Amazon a Cavendish kit. Like, I just thought, how hard could that?
In Texas right now that are setting up Jack's experiment to test it, doing that. So there are people that are going to test that
version or the more sophisticated one, because he kept pressing on the sophisticated one that involves changing his S with time as the experiment is being conducted.
I think that's something that we're going to need to do eventually. Yeah, but
that's true. But I just thought, why not do the simpler one first if it's easier?
Fair enough.
Yeah. Well, we can ask him. I could try and ping him and see if he wants to come on.
I think we all have his email.
So Dan, I have a question for you.
I think everybody in the world has his email at this point.
or
yes.
Emails from him.
Yes, it is the email, and it is the email list you cannot escape.
Dan, I have a question for you about your interpretations. Have you looked at, you brought up a wave, and you said, okay, a particle, and then there's an interaction, but everything else is waves. So have you looked at some of these interpretations or theories, kind of like there's one out there about that kind of hypothesizes that the universe is like a crystal structure, and we're just stuff. Yeah, kind of like that, where we're just the waves, and the interaction is between one wave and another, and that's where we see quantization is that interaction, and that has some analogies in Sachs's work. So I'm just kind of curious because that whole crystalline theory is something that's kind of new, but it's another interpretation of that, but literally taking the waves as waves.
Yeah, no, I'm not opposed to that. I've also been looking into a little bit like some of David Chester's work. I've been finding interesting. I've also been like dabbling with trying to figure out Weinstein's geometric unity. I think it's good to try to find the bits and pieces that everyone is getting right in each of these theories. Just so like, okay, well, if everyone agrees on this, then that's probably a pretty good pretty good axiom to start with, and we should take I don't want to limit other theories. Yeah, does that answer your?
Sure. No, I was just wondering if you had looked at that stuff, because I know you were looking at. There's a lot of interpretations of quantum mechanics.
Oh yeah, there's more than I got into. I just kind of went over like the 5 main most popular ones.
But I think you might find it interesting to let go of the whole particle idea, and just deal with matter as waves, because that's what
I agree. I don't think particles exist. I think particles are interactions between waves.
Yeah, and what we really know is the wave nature of matter. I mean, that's a well-known. It's something you can take an experiment or experience, and we know that.
That's
and it's anti-intuitive, but that's the reality.
Could you view particles? Could you view a particle as a vortice of wave energy? Would that be? Somewhat
a way
accurate?
that I've thought of particles before, as we were saying, is interactions between waves. Another way that I've kind of thought about it too is if we have solitons and waves, right? Perhaps particles could be some type of soliton.
That's kind of how I visualize it. That to me, that's the only way it makes sense. And then you get into stuff like spin, like spin 1/2, spin that are over or under 1, and it's like, well, yeah,
if you look at the Schrödinger equation, right? It's a wave equation. Then you get into, okay, I'm going to have it covariant. That's where you get into the Dirac, right? Equation. And with the Dirac equation and taking that further, treating that as an inertia, basically a matter field, is what the Sachs theory treats it as, and it's a matter field that pervades space, and so separate from the other fields that we're talking about when we talk about the EMF fields and the gravitational fields, but they're coupled, right? The inertial field is the source for the other fields, in that theory, anyway. But it's a can of worms, right? So once we say matter is waves, and we kind of admit that, it's a can of worms, because then all these questions, what's wave, right? It's just a huge, profound.
Yeah, exactly, and it's all encapsulated on field theory, because this idea of a field came from Faraday essentially, and then Maxwell was the guy who got the theory right, but Maxwell's interpretation was dropped off, and what we're left with is the mathematics of Maxwell. And so that's progressed to modern day, and now everything is described as quantum fields, but those are the underlying objects. But if, as you're saying, if things are waving, is there some deeper thing? So then what Tim was mentioning, I mean, if there is some medium underlying everything, then maybe the quantum fields that we currently see, maybe they're actually some solitonic excitations of some other underlying fluid or medium or whatever. Maybe it exhibits different phases.
And I guess to kind of get back into what Chris was saying about some of the crystalline structure of the universe, I didn't get into it today just because it's like getting into page looters is like a whole other can of worms. But I play mostly in Wheeler DeWitt, where with a cyclical universe, and I see time as an S1 fiber and a larger fiber bundle. And in that sense, when you have the timeless nature of that that page Wooter's quantization of time, it does become more of a crystalline structure where kind of everything's happening everywhere all at once. But so I'm kind of sympathetic to that, and to some degrees, Curtis, yes.
Well, guys, we're at the top of the hour, just about. Do you want to keep it going, or should we close things down for this evening?
I want to know if Jared. I want to know from Jared when that thing's going to jump up off the ground, so I can be watching.
Maybe tomorrow, maybe next year.
No, but not
real. I mean, really, you're going to run that test tomorrow? I'll call.
It's gonna wait until you're not looking.
Monday.
Hey Dan, what's your opinion? Just quickly like that. What's your opinion on the the pair production? So photons are converting into positron and electron and back and forth. And so obviously,
Like the giraffe.
obviously particles are apparent. The energy creates particle and back into energy and so on. So obviously mass. I had the idea that mass is related to somehow the charge, not the charge is somehow a mass, because if you have a positive charge and a negative charge, you add them together, it's equals zero, which creates which is what a photon is. So what's your theory on that? The pair production?
Like, are you asking if the pair production happens, or?
No, I know it happens, but what's your explanation of it?
In a nutshell, going off the Page Voodoo's approach with the Wheeler-DeWitt equation, in that kind of closed universe where everything does cancel out to equal zero, you can find, and again this is going to be where your dimensionality is e to the s, and then you find s based on the area. You can find a probability of it happening and where the energy comes from, because if it cancels back out, it doesn't really matter because the energy adds up to zero anyways. So I mean, like, you could come up with a finite amount of ways to cut that cookie depending on where the horizon is going to be for your system. But yeah, I don't see how there's any issues there though.
Okay, so but yeah, I just wanted to relate to the particle energy equivalence that you were talking about. So I'm just trying to link them with the pair production example. So yeah, so but for me, charge is can be related to mass, and mass is a charge and so on. But that's my opinion.
So Phil, that's one of the things. There's an experiment where they're going to be probing the vacuum, right, with the gamma rays, and I think that's
Was that the vacuum by fringe experiment?
Yeah, that's a very important experiment that will answer a lot of these questions where we're asking, okay, what is the vacuum, right? Is it a background pair gas where you have particle antiparticle pairs and they're coupled in a ground state, but their mass is still there, and that's what gives us our mass, our interaction with that density, or is it something else? Is it popping in and out, right? So
yeah,
that's going to be a profound data point that might lead the way, because, like I said, in the Sachs, in the background pair theory, it almost sounds like the same thing, right? Affecting the background pairs, splitting them up, you're lowering that permeability, right? You're almost, we're using different words for this, describing the same process, right? And that coupling, if that's what creates inertial mass, or that we measure, we can lower that, then we can, all of a sudden things open up,
yeah.
So that's an experiment I would watch closely.
How's it called again?
Vacuum by fringence.
Yes. Yeah.
No, yeah.
They're using gamma ray lasers.
Awesome. Yeah, that's going to be interesting.
Somewhat related to that, Curtis, also there's gravitational birefringence, or birefringent of gravitational waves, which I want to say the data is out there being collected. It hasn't been analyzed yet, but the data that LIGO has been collecting is suggesting positive confirmation of gravitational wave birefringence, which is huge because that fully supports, the ability that you can have, this bending space-time, right? We heard earlier, McCulloch doesn't really like bended space-time, but like if you have gravitational wave birefringence, you put the nail in the coffin for anything other than GR. Like,
well, it tells you there's more going on, and that we should take Einstein's prescription more seriously, right? So, that's the big question. What do we do now? We know time and space reflection symmetry is a thing. Einstein did not know. He was gone before that came out. So what would he have done? Okay, that's the question, right? But how deep does that go? I don't know. Where you just take that. What's the next symmetry you can take? You can keep adding things, right? With the math, and there's you can go to the nth degree, but you could probably get too complex, right? It's not a Clifford algebra of infinite. It's going to be something in the middle, but who knows?
But
where.
if you can demonstrate gravitational wave birefringence, as a physical phenomenon, then the next thing becomes, can you generate gravitational wave birefringence?
All right, what is this? What are you talking about?
So birefringence, right? Stretched lattice. So waves one way, slower, waves the other way, faster. So if space-time, as a fabric of space-time, right? If you have a black hole or something that's really stretching on that space-time, and you have a gravitational wave that goes through it like, an angle, off angle to us, by the time it gets to us, it's going to have two components to it that are not perfectly orthogonal, right? It'll have a little bit of polarization on it. And so now you know that gravitational wave is going in one direction faster than it's going in another direction. If you can show that you can make a gravitational wave go in one direction faster than in another direction, you're showing that gravity is, first off, it relies upon space-time for propagation, because space-time is affecting its propagation, because we see bent space-time is affecting, its ability to propagate fast, slow. The other thing is...
Hang on. So you're saying, the black hole eats a neutron star, some nonsense thing way, way out there. The wave that comes to us is going to hit us perpendicular. So it's going this way, and it's going in and out at the same time. So it's a three-dimensional wave that's going to smack into us. You're saying that it's possible that it's moving this way at a different rate than it's moving this way?
I want to say that LIGO doesn't have the capability for enough accuracy to be able to perfectly do it. But TESS, which is the satellites that are like 1 million kilometers apart, pointing lasers at each other, those ones should have the resolution to be able to accurately identify gravitational wave birefringence, because this wave, right, has a wavefront on it, and that wavefront is like curved a little bit or something, right? So it's going to hit one before it hits another if they're both, simultaneously there, right? And the idea is that if this wave is been split into its two parts, so birefringence, what's happening is your wave is getting split into two different polarizations, right? You have your ordinary wave, the one that's going through normally, and then you have your extraordinary wave, which is traveling at some changed speed because of a change in the property of the material.
Wouldn't there be, if you're saying that the wave can be broke into multiple components, wouldn't there be an infinite number of multiple components? The universe doesn't know what 90 degrees is. Everything is 90 degrees.
You have vertical horizontal polarization, right? And you have circular polarization. Those are the two polarizations.
Well, by the way, that's a reference to electromagnetic waves if you say that, right?
Well, you can
help me out here, Nathan. I'm way out of my depths on this one.
You can still make the analogy. You can have linearly polarized or circularly polarized photons and gravitational waves. But yeah, I mean, the gravitational ones are two tensor, but I mean, there's still two states, like this notion of left and right or X and Y. I mean, this idea of something propagating in the Z direction and then there being two perpendicular directions where some transverse component could be. I mean, that concept still occurs.
True.
But let's see, what were we talking about more specifically, I guess?
And I think to clarify for Drew, because it sounded like you were making a reference to like the electric field versus the magnetic field, just like from how you were gesturing. I don't think that that's actually what would be going on. I think it would be more follow like the K vector, just the direction of propagation. And I think the idea would be that like if you have a source of gravitational waves, for instance, and you happen to be at this location, the K vector that you observe might be slower or faster than if you were over here at this location, where the k vector, or at least the component of the k vector towards you over there, yields a larger or smaller speed. So it's not that the two disturbances that are perpendicular to each other, like in the context of electromagnetism, the electric field and the magnetic field, it's not that those two, fields propagate at different speeds, but rather your position around the source observes a different wave speed depending on where you are.
Sure.
I gotta take off, guys. So I do appreciate everything. You guys have a good night.
I gotta go too.
Thanks, Dan.
Bye.
Nathan,
Y'all have a great evening.
I just finished catching up with all the presentations, and I was really impressed with the math that you threw at the problem there. That was awesome. I had a question about boundary conditions between. So you proposed this new gauge for looking at gravity, I guess, in GEM. What would the boundary conditions for that look like between matter and vacuum? Out of curiosity.
That's a really good question, and I've explored that quite a bit, although not as much as other aspects of the research, because that question requires that there would be, let's say, for instance, substantial refraction or reflection that would occur. And as it stands now, from what we found, we don't seem to find that any known material other than like neutron star material, which we don't have handy in the lab, would have a substantial impact on gravitational waves. The only thing that's promising so far that we're working on right now is I came to notice that if you use a superconductor and you apply an electromagnetic wave and you provide just the right frequency and amplitude so as to, in some sense, synchronize with the gravitational wave that comes in, you could, in principle, cause a reflection, in which case then you would have like a reflection coefficient and things of that nature. And you could develop the boundary conditions, the mathematics. I wrote it all out. It's already there. But of course, I ran out of time in our 1 hour slot. So my hope is that anytime I'm invited again, I'm just going to sort of like to be continued from the last one. So in other words, I'm sort of done with harmonic gauge and why we don't want to use that. Now I'm on this Helmholtz decomposition and why it's superior. So now next time I'll show how does it yield boundary condition results on a normal conductor, on a superconductor, if you also include electromagnetic waves. And so basically what you're asking is sort of like what you would see in a part 2.
Awesome.
Yeah, no,
awesome.
Nathan, you were welcome. You were absolutely welcome. Come back anytime, man. Come back anytime.
For sure. And more towards that point, I was thinking of some devices I had seen in other presentations, more for extraction of energy than for propulsion or anything. But I saw that you mentioned that modes corresponding to accelerating masses don't necessarily propagate, but modes corresponding to stress propagate.
Yeah, that's true. You need a quadrupole stress, which is kind of like a standard textbook general relativity formulation. Like you can find it like in Misner, Thorne, and Wheeler or Carroll's book, or any of them will show you that there's a very straightforward calculation that shows that all other degrees of freedom other than quadrupole, like higher order degrees of freedom, like monopole and dipole radiation wouldn't be possible. Quadrupole would be the lowest order that you could have, and it comes from the stress tensor. Not meaning the spatial part of the stress tensor, not the time part or not the energy density or momentum density, but specifically from the spatial components of the stress tensor.
Got you. So you're having with this quadrupole moment, you're okay. I kind of see where that's going. Well, maybe what I was thinking of wouldn't work in the context of gem theory, but what if you imagine having a Casimir cavity,
Mhm.
and very, very quickly, like imagine one of the plates you're using in your Casimir cavity
Yeah.
is effectively a transistor, a very large flat transistor. So you can effectively switch off the conductivity. You can go from insulating to conducting with one of the plates at some really, really high frequency, whatever the switching frequency can be, megahertz, maybe even gigahertz. So the Casimir cavity has some reduced vacuum noise. So that would be in the stress energy tensor, and you can feel that as a force. So by very rapidly modifying the boundary conditions, by modifying your electrical conductivity in that case, would that sudden change in the Casimir situation at that surface, would that propagate far field gravity stuff potentially?
Well, okay, I'll make a couple comments about it because I am very interested in the Casimir stuff also. I'll say, number one, if you're going to dynamically like modulate the system, then you are going to be looking at like a dynamical Casimir effect versus like the static Casimir effect, right? Just as a side note. But I'm sure you must realize that this is all going to hinge on reflection of the gravitational wave inside, because as it stands now, it's believed that practically everything is almost completely transparent to gravitational waves. So before I invested myself more deeply into developing the formalism for gravitational, static or dynamical Casimir effects, I felt like the starting point really was to dedicate myself to the possibility of reflection of gravitational waves. That seems like it's the natural starting point, right? But
so just to clarify, I guess you're just going from the more standard GR space-time curvature approach, not from a polarizable vacuum sort of approach, I guess.
That's okay. So that's another layer. You're reminding me actually that when I was working with Raymond Chow on the PhD, there was a project that we were looking at, and DARPA was funding us, and it involved generating a gravitational laser, which in some sense can be likened to the Casimir effect, in that the bottom line is you have to have a quantum vacuum fluctuation, like you have to have a ground state energy that you amplify, like a parametric amplification. And I would tell Ray, like quite frankly, if that were to work, I think it deserves literally like 5 Nobel Prizes, because now you've proven the graviton exists. You've made it possible to reflect gravitational waves off of a material. You've parametrically amplified it into a laser. And, and I think I had like 2 more that came to mind that I was like, so I felt like it's a house of cards, where if just one of those is not true or can't be done, the whole thing would collapse. So I felt like a more modest goal is try to find a way to reflect gravitational waves, that alone, or transduce them, because we look a lot at communication. So that's really our focus right now, actually, is can we communicate with gravitational waves? And so Ray spends a lot of time on transduction between gravitational and electromagnetic waves, which can arguably be done classically, doesn't rely so much on quantum, although the models that he proposes tend to be quantum. So all I'm saying is like the gravitational Casimir effect is like a basket with like several eggs that are delicate. And I mean, to even get one of those to hatch is like, would be amazing. Like if you could reflect gravitational waves, that would be amazing. I would think.
Got you. And it looks like maybe superconductors can do some parametric amplifications, possibly. Or
that's been the hope.
So also, so you were saying it was reflecting gravity, or maybe doing some flux pinning to gravitomagnetic fields or something. But so yeah, I mean, it looks like the gravity is going into the surface with some penetration depth. So with that sort of interaction, yeah, you should be able to modulate the material properties with respect to time resonantly. And I guess, is that what you're saying?
Yeah, like what I presented today, which it was only like the last like 10 minutes of the talk, where I said, oh, look, here's one way you could use this formalism. You could apply it to a superconductor, identify a plasma frequency, an index of refraction, a penetration depth, and all of that good stuff. But when you put the numbers in, that's the bottom line, right? And so when you put the numbers in for just a plain old superconductor, it's still hopeless. But what I found, as I was mentioning just moments ago, I found that if you introduce high power electromagnetic waves in addition to the gravitational waves, it then becomes hopeful. But that's yet to be scrutinized. I hope that if I have an opportunity to present that, and if you guys scrutinize that, that would be super helpful, because we are seeking funding. We are working in that direction. Investors are interested, and it would be great to be able to actually present something that will, obviously work and produce results and move us forward.
And then the last question I had as well. I was just excited to hear it. So you were saying maybe near electromagnetic fields can propagate gravitational waves somehow.
Oh, are you talking about, so I think David Chester commented on that part. It was the part about where I was looking at like the geodesic equation of motion with electromagnetic coupling thrown in there. Is that the part you're talking about?
Yeah, I believe so. I have a few ideas about that. I wanted to like throw and see what sticks,
Yeah.
But go ahead. You were saying something?
Oh, no. I was just clarifying. Is that the part of the talk you're talking about where
I believe
I
so,
just
yeah.
basically looked at Lorentz force and curved spacetime?
I believe so.
Yeah.
So that, yeah, I mean, we have a few ideas about how to potentially test that particular, or at least we have some ideas about a device maybe that could generate that sort of output if there's measurement devices for it.
Oh, are you working in a lab?
Yeah, yeah, I've got a lab going.
Oh, wow, great.
Not at the lab at the moment, but
Sure.
yeah.
Oh, well, if you're interested in, I was telling David this by email that we're very open to inviting those who are interested in the stuff we're doing, and maybe mutual collaborations and that would benefit each other. And so like we actually put together a meeting for Friday the 22nd, where a number of physicists as well as investors and such are gonna get together. Raymond Chow will share his idea, and we'll open it up for questions. I was scheduled to talk, but then we decided we'd probably just let Ray handle it, because he's the big, he's the famous guy. You know what I mean? So he's got the weight. If you've heard of him, by the way, he's well known in quantum optics. He wrote a textbook on it, and he was a professor at Berkeley for almost 40 years, and did his doctorate at MIT and all that good stuff. So he's a brilliant physicist. He actually worked with Charles Towns, who was given the Nobel Prize for inventing the maser, which became the laser. And my favorite part of his story is he was advised by John Wheeler during his undergrad to. I guess he always tells the story. Ray's along in years, and so he's got lots of great stories. He always tells the story about how when he went to John Wheeler and asked, "What would you like me to do?" John Wheeler said, "Go quantize gravity. That's your thesis project." It's like, okay,
Nice.
Sure.
Yeah, that's quite the pedigree. By the way, Tim, is Drew still around? I wanted to say hi. Well,
no, I think Drew left, and I'm just keeping things going until you guys are done, and then we can close the conference down for the evening.
Email me, Michael, and that way, if you want to follow up and see if there's mutual interest and stuff, we can follow up that way too.
Certainly. I think, yeah, David, Chester, and I both have ideas that would potentially be relevant. We'll see what's feasible.
Cool.
And yeah, I think in terms of
I just emailed both of you, so you'll have the others.
Oh,
thank you.
Sorry, what was that, Tim?
Oh, I'm sorry. I emailed both of you. Sorry, my AirPods died, so my sound is different.
Gotcha. So yeah, Nathan, I would say maybe maybe some of those additional like coupling terms or to electromagnetism might make it for easier engineerable stuff than parametric.
That's exactly what I was hoping, is that, you know, just small tests of novel gravitational effects that we haven't seen before would be great to get our feet wet. You know, I mean, I'm not aware of anything being measured beyond gravitomagnetic field. I mean, have we seen like a Faraday-like effect ever? I don't think so in the lab, like a gravitational Faraday effect.
Yeah, I mean,
I don't think so.
these equations lead to many possible tests.
Exactly, of which like so few have ever been observed.
Yeah, I think that the near field test, we would basically we would need access to a sensitive interferometer similar to the LIGO detector, but smaller would work. Something like that, or if someone else has a way that they've proven of measuring higher frequency gravity waves, maybe that would work.
We've actually looked at the patents that already exist out there. There was a few, but none of them ever bore fruit. So we ourselves are trying to go in that direction.
Yeah.
Well, that's the thing. I mean, LIGO is one of the most expensive experiments of all time. I mean, the whole gravitational wave thing got started by, was it someone named last name Weber, who had a claim for a gravitational wave detector, but it's not clear if
the
it
Weber
worked
bar
or not. Yeah, right.
Oh well, he said it did, but no.
Yeah, so there is a lack of
did.
consensus in the community if that was real or not. So it was enough inspiration, surprisingly enough, to eventually get LIGO built. But in terms of doing research to try to reproduce other types of detectors, it's kind of considered taboo. It's a little almost fringe sounding, even though.
Wasn't it based on Bondi's sticky bead argument from the '57 gravity conference at Chapel Hill?
LIGO
might have
not really LIGO.
No,
Maybe.
the Weber bars, the concept.
Oh, yeah, that one would be, yeah.
Well, generally speaking, the idea that gravitational wave could actually transfer energy in some way, shape, or form was the sticky bead argument, right?
By the way, didn't we have a speaker a few months back that was trying to do some kind of a different type of gravity wave detection?
Yeah, that was Ray. Yeah. He had the two. They were the two superconductors, and they were suspended, right? So you had the magnetically levitated superconductors, and what was it? When a gravity wave hits, because they're quantum, they would dovetail into each other, and you could detect.
Yeah, they were actually spins.
Wasn't
They were
even
electron spins.
superconductors. It was a Magnon Bose-Einstein condensate in a yttrium iron garnet sphere.
You're talking about Ray Chow?
Yeah.
Correct.
No, there was a different speaker we had. I got to look it up. Trying to remember.
Well,
anyways, we have a presentation here.
That's all I wanted to mention as well. So I'll probably.
Thanks, Michael. Appreciate that. Let's follow
Yeah,
up.
Michael. Thank you.
And Curtis also still reading those papers, still learning stuff.
Sure.
Also got the startup company and all sorts of things. So it's going to take some time. But
are you starting up a company, Michael? Are you starting up a company?
Yeah, well, I mean, testing all this stuff. Also just doing other material science work. We have some really good silver ink that I'm going to get back on working soon. So that's
very nice.
Yeah, that's one of his many projects. Well, guys,
you mentioned superconductors, and it's on a lot like Ning Ling's work. I don't know if you're familiar.
Yeah, I am. Isn't she the one that like mysteriously disappeared or something like that?
She didn't really disappear. I think she stayed, if I remember correctly, she was in Huntsville the whole time. She just kind of dropped out of the media. But I believe, and somebody just published a story on her. She passed away of cancer, I think, a few years ago. So yeah.
She did good work though, and supposedly she got positive results, but then it all went like Black Project style after that. So we don't know how much she eventually found.
And
there was a YouTube video back, I think Thursday. The Sandbox did one on her.
That's the one I'm thinking of. Yeah, the very recent one. They talked to her son. They were able to track her son down, and he talked about her a little bit. So those missing years.
That she had superconductors and weighed masses above them, and apparently it didn't matter what the material was or the mass, that she got a weight reduction.
Yeah. And then she
Oh.
also had what was she calling AC gravity, right? Where she thought she could increase or decrease it, in contrast to Poklanoff, who in his thing, he had the rotating superconductor, and he said there was a column of reduced gravity above it. And if I remember correctly, her thing was she felt that by using the same equipment and modifying it, you could increase or decrease it. But
And that actually agrees perfectly with what Nathan was saying, because if you have the superconductor, it doesn't do enough, and then if you introduce like high frequency AC magnetic fields, high intensity at least, then
Yes.
that gets things interesting, and that's exactly what apparently she found. So that's exciting.
Really?
Yeah.
Yeah.
In fact, and it was all like, I don't know if it was DARPA or some other, but she was definitely in Huntsville at the, so that's where all that stuff goes on.
Yeah.
Wow.
Yeah.
So Nathan, you're probably going to find that there's nothing new that
nothing new under the sun. Exactly.
I
Yeah.
know.
No, but that's
did-
it's good. It's good these are like little what do you call them? Like way markers, right? Like when you're climbing
yeah,
Everest,
yeah.
you see little flags, it's like, okay,
Yeah,
someone's
people-
been here.
Yeah, that's
You know?
true. I wrote a really, really extensive paper on this a couple years ago. It had a couple hundred references, and I really did my due diligence. So I knew about her, but I didn't know about the idea of using high intensity electromagnetic waves to assist the process.
Well, it's in the name, AC gravity, and then she was.
Oh, I hadn't heard that name.
Yeah, that was her company that she started supposedly doing this sort of
Oh,
stuff.
that was the name of her company.
Yeah, and then she was like spinning
And-
these discs and seeing a gravitomagnetic interaction supposedly.
Yeah.
And then AC gravity. That, I mean, it kind of tells the story,
Yeah.
Oh, yeah.
Yeah. Well,
That is
guys,
interesting.
should we close things down for this evening?
Sounds good.
Yep.
Okay.
Yeah.
Well, thank you.
Excellent-
This has
excellent
been
job, everyone.
This has been APEC for March 16th, and I want to give all of you guys an applause. Thank you so much. Thank you so much. This is an amazing, you guys have made this an amazing conference. Thank you again.
Thanks to all the speakers.
Awesome, guys. Thank you.